The smallest distance that means anything in physics sits so far below the size of a single atom that comparing the two is like comparing a marble to the entire size of planet Earth. The largest structure ever confirmed to exist is a wall of galaxies so wide that light needs roughly 10 billion years just to cross from one end of it to the other, nearly the entire age of the universe itself. One of those two facts fits inside a single proton. The other barely fits inside everything we can see. Tonight, we're going to cover the whole distance between them, starting with the smallest measurable thing in existence. What's actually down there, underneath a single atom? An atom is built almost entirely out of nothing. Let's start with a hydrogen atom, the simplest one there is, one proton at the center and one electron somewhere around it. The proton sits at a radius of about 1 femtometer, a distance so small you'd need 15 zeros after the decimal point just to write it down in meters. The electron, on average, orbits roughly 100,000 times farther out than that. If we scale the proton up to the size of a marble, about 1 centimeter across, that electron ends up circling somewhere near the far edge of a sphere a kilometer wide, the better part of a small town built around one tiny ball at the center. Everything between the marble and the edge of that town is empty. No floor, no walls, no faint haze of matter thinning out gradually. Just space, doing nothing, holding nothing. In the first decade of the 20th century, the standard model of the atom, proposed by Joseph John Thomson, treated it as a small sphere of positive charge with electrons scattered through it, something closer to a pudding with fruit embedded in it than a marble in an empty town. To test that model, Ernest Rutherford had two researchers, Hans Geiger and Ernest Marsden, fire a stream of fast, heavy particles at an extremely thin sheet of gold foil. Under Thomson's model, we'd expect every particle to pass straight through with at most a slight wobble. Since the positive charge was supposed to be spread out and weak, almost all of them did exactly that, sailing through as if the foil were barely there. But a small fraction, roughly 1 in every 8,000, bounced backward at sharp angles, some of them nearly straight back the way they came. That result didn't fit the old model at all. A diffuse, evenly spread atom has nothing dense enough to bounce anything off of. Rutherford worked out that the only way to explain what Geiger and Marsden were seeing was if almost all of an atom's mass and all of its positive charge were packed into one tiny core with the rest of the atom close to empty. We didn't guess the marble and the empty town. We measured them. If we run that same ratio in 3 dimensions instead of 1, the emptiness gets more extreme, not less. The electron sits roughly 100,000 times farther out than the proton, so the volume of space it sweeps through works out to about 100,000 cubed, which lands at roughly 1 quadrillion. 1 quadrillion. Out of every quadrillion cubic units of space inside a single atom, only about 1 of them contains anything solid. The rest is open. That isn't unique to you. It's true of the chair under whatever you're sitting on, the phone in your pocket, the ground under the building we're all standing on. Multiply it across the roughly 7 octillion atoms, making up an average human body, and the proportions stay exactly as lopsided. Squeeze every nucleus in your body together, closing every gap completely, and you would not lose a single atom and you would not weigh any less. Mass doesn't care about space. You would compress down to something about the size of a single red blood cell, a speck that needs a microscope to see it all. Same weight you have right now. A city's worth of empty space, simply gone. Pack matter that tightly, at the density of a nucleus itself, and a single teaspoon of it would weigh more than 1 billion tons, heavier than most mountains we could name. We've just shown how little of an atom is solid. None of that emptiness, though, is the reason your hand stops at the surface of anything you touch. The actual reason is electric. Every electron carries a negative charge, and the outer electrons in your skin meet the outer electrons of whatever you're touching edge to edge, long before either nucleus gets anywhere close. Negative charges repel each other, and that repulsion grows sharply as the distance between them shrinks, fast enough to stop your hand cold within a fraction of a nanometer. There's a second rule working alongside that one, with no everyday version we can compare it to. Two electrons are forbidden from occupying the exact same quantum state in the exact same place at the exact same time. Push them too close together, and that prohibition pushes back on its own, even before the electric repulsion fully takes over. Wolfgang Pauli worked out that rule in 1925, originally to explain patterns inside individual atoms. It turned out to apply at every scale matter shows up at. The same exclusion holding your hand above a table is also the only thing holding up a dying star once it runs out of fuel to fight gravity with. It's a strange thing to learn that solidity, the feeling we trust more than almost any other, has nothing to do with anything actually being solid. That still leaves the one part of the atom we haven't opened yet, the part that isn't empty. The proton itself, the marble at the center of that kilometer-wide town, isn't a single solid thing either. Pack three smaller particles together. Bind them with a force that doesn't resemble the electric repulsion we just described, and you get something that behaves like one object only from a distance. Get close enough to the marble, and it stops being one thing too. What's actually holding it together? The proton isn't one thing, it's three. Two up quarks and one down quark, each one a genuinely fundamental particle, with nothing smaller found inside any of them no matter how hard we've looked. Add up their masses and the numbers are almost embarrassingly small. The two up quarks come in at about 2.2 million electron volts each. The down quark adds roughly 4.7 million more. All three together land at just under 9 million electron volts, give or take. A proton's actual mass measures out to 938 million electron volts. Do the division, and the three quarks account for less than 2% of the proton's total weight. More than 98% of what you'd weigh if you were made purely of proton mass isn't quark at all. It's something else, locked inside the same tiny space. A neutron is built almost the same way, just with the proportions flipped. Two down quarks and one up quark instead of two up and one down, which is enough to shift the total charge from positive to exactly zero. The numbers work out almost identically too. Add the three quark masses together, and you still land somewhere under 1% of the neutron's actual weight. Whatever is filling in that missing mass, it isn't picky about which combination of quarks it's holding together. We didn't always know protons had parts. For decades, physicists treated the proton and the neutron as the smallest pieces of the nucleus, full stop, nothing further down. That changed in 1964, when Murray Gell-Mann, and independently George Zweig, proposed that protons and neutrons were themselves built from smaller particles. Gell-Mann had already spent a few years organizing the growing zoo of newly discovered particles into repeating patterns, a system he called the Eightfold Way, and the quark idea was what finally explained why those patterns existed at all. He borrowed the name itself from a nonsense word in a novel by James Joyce, and it stuck even after the joke behind it was mostly forgotten. The proposal stayed mostly theoretical until 1968. When a team at the Stanford Linear Accelerator, led by Jerome Friedman, Henry Kendall, and Richard Taylor, fired high-energy electrons at protons and watched how they scattered. If a proton were a smooth, uniform ball, the electrons should have deflected gently, in small, predictable angles. Instead, some of them bounced back sharply, the same kind of result that had revealed the nucleus itself half a century earlier. Something small, hard, and concentrated was sitting inside the proton, scattering electrons the way a few hard pebbles scatter a stream of water. We had found the quarks, even though nobody has ever managed to pull one out and hold it on its own. Up and down aren't the only kinds of quark, just the only two stable enough to matter for anything you're made of. Physics has found 6 quark types in total: up, down, charm, strange, top, and bottom. Discovered in pairs between the 1960s and 1995, when the top quark, the heaviest by far, was finally confirmed at a particle accelerator outside Chicago. The heavier 4 don't last. They decay back down to up and down quarks within fractions of a second, which is exactly why every ordinary atom in your body, in this room, on this planet, is built from only the 2 lightest types. The other 4 show up only briefly, inside accelerators, recreating conditions the universe hasn't experienced naturally since its first instance. That instability is one thing. The force holding the stable ones together is another. And it isn't an accident of bad equipment. It's the whole point. Every other force we know gets weaker with distance. Gravity does. Electromagnetism does. Pull 2 magnets apart, and the pull between them fades fast, the farther you go. The force holding quarks together does the opposite. It barely shows up at extremely short range, almost as if the quarks were nearly free, then ramps up sharply and settles into a steady, constant pull that never fades, no matter how far apart you try to drag them. Physicists have actually measured that pull. It holds at right around 16 tons of force, locked in place, as if every quark were tied to its neighbors with a leash that never goes slack, regardless of how far you've already pulled. Electromagnetism is carried by photons, and photons don't interact with each other at all. 2 beams of light can cross directly through one another without so much as a flicker, because photons carry no electric charge of their own. Gluons, the particles carrying the strong force between quarks, are built differently. There are 8 distinct types of gluon, and each one carries color charge itself, the same property they're supposed to be mediating between others. That means gluons interact constantly with other gluons rather than passing through empty space untouched. Instead of spreading out evenly in every direction the way an electric field does around a charged particle, the gluon field between 2 quarks gets pulled inward on itself, squeezed into a narrow tube instead of a spreading cloud. Stretch that tube, and you're not thinning out a field, you're lengthening a string, with the same tension running through it from end to end no matter how long it gets. That's the actual mechanical reason the pull never fades with distance the way every other force in this story does. Try to actually pull 2 quarks apart, past that point, and something strange happens. You'd expect that with enough force, eventually they'd separate, the way pulling hard enough on a rope eventually gets one end away from the other. Instead, the energy you're pouring in keeps building inside the stretching tube between them, like winding a spring tighter and tighter with no place for the extra energy to go. Eventually, there's enough energy stored in that stretched connection to do something else entirely. It converts directly into a brand new pair of quarks, one matter, one antimatter, snapping into existence right at the breaking point. So you never end up holding a single free quark. You end up holding 2 pairs instead of 1, each pair just as bound as the original. This is exactly what particle accelerators see today. Smash 2 protons together hard enough, and instead of spraying out free quarks, detectors catch tight, narrow sprays of new particles, called jets, sometimes dozens of them, the visible signature of this exact snapping and pair production happening on an impossibly short timescale. Get close enough instead of far enough, and the same force almost vanishes. At extremely short distances, quarks behave almost as if they're free particles, barely tugging at each other at all. David Gross, Frank Wilczek, and David Politzer worked out why in the early 1970s, and the discovery earned all 3 a Nobel Prize decades later, in 2004. They called the effect asymptotic freedom. The closer quarks get, the less they notice each other. The farther apart, the harder the universe holds them together. None of this reaches you directly, day to day. And there's a real reason for that too. Quarks carry a property physicists call color charge. Nothing to do with actual color, just a label for three types of charge the strong force responds to, usually called red, green, and blue. A proton works because it combines exactly one quark of each color, and the three cancel out completely, the same way mixing red, green, and blue light produces plain white. Gluons can also pair a quark with its own antimatter twin, an antiquark, carrying the opposite color, which cancels out the same way. Every stable particle built from quarks follows that same rule. Color charge always balances to nothing on the outside, no matter how violent the force is doing the balancing on the inside. That cancellation is why the strong force barely leaks beyond the nucleus itself, fading to almost nothing past a couple of femtometers. We live our entire lives surrounded by a force running at roughly 16 tons at its core, and we never feel a trace of it, because by the time it would reach us, it's already been almost perfectly cancelled out. All of that, the quarks, the gluons, the constant tension holding everything together, accounts for less than 2% of a proton's actual weight. The other 98% has to come from somewhere. Where does mass like that actually come from, if it isn't sitting inside the particles supposedly carrying it? None of that missing mass is hidden somewhere we haven't looked yet. It's not extra particles, and it's not some undiscovered piece of the proton waiting to be found. It's energy, pure, ordinary energy, converted into mass through the same relationship Albert Einstein worked out in 1905, the one connecting energy and mass directly, with nothing extra needed to make the conversion work. Inside a proton, the three quarks are moving at close to the speed of light, constantly, and the gluon field stretched between them carries real tension, the same 16 tons of pull we measured a moment ago. Both of those, the motion and the tension, count as energy. Energy has mass, whether or not anything solid is sitting still to carry it. Add up the motion and the tension trapped inside a proton, convert it through that same relationship, and you get the missing 98%, accounted for, with nothing mysterious left over. The quarks themselves, before any of that motion or tension gets added, still carry a small amount of mass purely their own, 2.2 million electron volts for an up quark, 4.7 million for a down quark, 500,000 for an electron, which isn't built from quarks at all and isn't bound to anything else, sitting there with mass of its own regardless. None of that comes from confinement, motion, or tension. It's just there, built into the particle from the start. Where does that baseline amount actually come from? The equations describing how particles interact work most cleanly when every particle involved is massless, a property called gauge symmetry, and breaking that symmetry by simply inserting a mass by hand wrecks the whole structure. That was a real problem, because by the 1960s physicists already knew some particles definitely weren't massless. The W and Z bosons, the particles that carry the weak nuclear force, the one responsible for radioactive decay, were predicted to be enormously heavy if they existed at all, somewhere between 80 and 100 times the mass of a proton. A massless theory had no room for particles that heavy. Something was missing from the equations themselves. In 1964, several physicists working separately arrived at the same fix within months of each other. Peter Higgs proposed it. So did Robert Brout and Francois Englert. Working together, and separately Gerald Guralnick, Carl Richard Hagen, and Tom Kibble. The idea was a field, now called the Higgs field, that fills every point in space, including the empty vacuum, and never switches off. Most fields drop to zero in a vacuum. This one doesn't. It sits at a fixed, Non-zero value everywhere, all the time. And every particle moving through the universe is also constantly moving through it. Picture wading through water instead of walking through air. Some shapes barely notice the difference and glide through with almost no resistance. Others catch the water hard and have to push against it with everything they've got. The Higgs field works the same way, except the resistance isn't water. It's a genuine interaction between the field and the particle passing through it, and that interaction is what we measure afterward as mass. A particle that barely interacts with the field, like the electron, ends up nearly weightless. A particle that interacts strongly, like the top quark, the heaviest fundamental particle ever measured, at about 173 billion electron volts, roughly as heavy as a single atom of gold, ends up carrying enormous mass instead. The photon doesn't interact with the field at all, and stays exactly massless, the way the old equations always wanted everything to be. The strength of that interaction has an actual name, a coupling constant, and it isn't predicted by the theory itself. Physics can explain why interacting with the field produces mass. It cannot yet explain why the electron's coupling is so much weaker than the top quarks, only that it measurably is. That gap is one of the genuinely open questions in modern physics, not a subtle detail, an honest one. There's a subtlety in how the field manages to give particles mass without simply breaking the equations it was supposed to fix. The Higgs field doesn't destroy the underlying symmetry physicists needed. It hides it. Imagine balancing a pencil perfectly upright on its tip. While it's standing, the setup is symmetric. No direction is favored over any other. The moment it falls, though, it has to fall in some particular direction, and once it lands, the symmetry is gone, even though nothing about the original setup changed. The Higgs field works on the same principle, settling into a particular, non-zero value rather than balancing at zero, the way water finds the bottom of a basin rather than balancing on the rim. The symmetry stays true in the equations. It just stops being true of the universe those equations describe. All of this happened, in cosmic terms, almost immediately. For roughly the first trillionth of a second after the universe began, it was still hot enough to keep the Higgs field balanced at exactly zero, and none of this mass existed yet, not in quarks, not in electrons, not anywhere. As the universe cooled past a specific threshold, the field dropped into its non-zero value all at once, everywhere, in an instant. Every particle that has carried mass since has carried it because of that one transition, completed before the universe was old enough to measure in anything but fractions of a second. The W and Z bosons themselves weren't only theoretical numbers on a chalkboard by the time any of this got tested. Carlo Rubbia and Simon Vandermeer led the team that detected both particles directly in 1983. With masses matching the prediction almost exactly. The Higgs boson was the harder, slower piece to catch, the one still needed to explain why those particles had the masses they did in the first place. That was the proposal. Confirming the field itself took almost 50 years. If the Higgs field is real, disturbing it should produce a genuine particle of its own, the way disturbing the surface of a pond produces a ripple you can actually observe. That particle, the Higgs boson, was finally found in July of 2012 by two independent detector teams at the Large Hadron Collider, each one analyzing the debris from trillions of proton collisions without coordinating their results in advance. Both teams found the same thing in the same place, a new particle weighing about 125 billion electron volts, roughly 130 times the mass of a single proton. Peter Higgs and François Englert shared a Nobel Prize the following year. Robert Brout had died a year earlier, and the prize cannot be awarded after death. So the honest answer to where mass actually comes from has two separate parts, not one. Almost all of the weight you'd measure in any ordinary object, your own body included, comes from motion and tension trapped inside protons and neutrons, energy converted to mass, the way we worked out a few minutes ago. The Higgs field barely touches that part at all. What it explains is something much smaller and much stranger. The tiny baseline mass that quarks and electrons carry before any of that confinement energy ever gets added, the seed value the rest of physics builds on top of. Mass, in other words, was never one single thing to begin with. Most of it is borrowed from motion and force. A small remainder is borrowed from a field that fills all of space and never turns off. There's something almost funny about it. Even your own resistance to being pushed, the most basic feeling a body has, isn't really yours. Almost none of it was ever sitting still, waiting inside you, to begin with. If mass itself can be borrowed rather than built in, matter starts to look less like a fixed collection of things and more like a temporary arrangement of energy and interaction held in place for now. That raises an uncomfortable question about how far this goes. How small can something get? How many times can it be divided before the very idea of dividing it stops meaning anything at all? Combine the three constants that show up most often in physics, the strength of gravity, the basic unit of quantum uncertainty, and the speed limit on everything in the universe, and the math produces a single length on its own, without anyone choosing it. That length comes out to about 1.6 times 10 to the negative 35th power meters, a distance so small it needs 34 zeros after the decimal point before any real digit shows up. Physicists call it the Planck length, and it sits roughly 16 orders of magnitude below anything any particle accelerator on Earth has ever directly probed. Max Planck worked out that number in 1899, decades before anyone understood quantum gravity well enough to know why it might matter. He wasn't hunting for the smallest possible distance in the universe. He was looking for a system of units that didn't depend on anything human. No meter defined by an old metal bar in France. No second defined by how fast the Earth happens to spin. Combine those three constants, and you get units any civilization anywhere would arrive at independently, built from the universe itself rather than from convention. The fact that this same number turned out to mark something physically important took most of a century longer to understand. The same three constants produce a matching unit of time, the time light needs to cross one Planck length, which works out to about 5.4 times 10 to the negative 44th power seconds. They also produce a matching unit of energy, somewhere around 10 to the 19th power billion electron volts. The Large Hadron Collider, the most powerful accelerator ever built, the same machine that caught the Higgs boson, reaches barely a quadrillionth of that energy at its absolute peak. These aren't three separate numbers picked to look impressive together. They're one consistent package, describing the same boundary measured three different ways. Here's why it matters. Probing anything this small works the same way it did for the quarks inside a proton or the nucleus inside an atom, by aiming something with a short enough wavelength at it and watching how it scatters. A wave's wavelength only gets that short by carrying more and more energy. The same trade-off behind every microscope, every particle collider, every experiment in this entire story so far. Push that trade-off far enough and something strange happens. The energy itself becomes massive enough, concentrated in a region small enough, to trigger its own gravitational collapse, forming an event horizon around itself before you ever get a useful measurement back. You'd need a black hole to probe the distance, and the black hole would swallow the very measurement you were trying to take. That isn't a limitation of current instruments. It's a limitation built into combining quantum mechanics and gravity at all. This is also exactly where the two best-tested theories in physics stop agreeing with each other. General relativity treats space and time as smooth, continuous, with no minimum unit built in anywhere. Quantum mechanics insists that at small enough scales, everything fluctuates, position included, governed by uncertainty rather than fixed values. The other quantum theories in this story, the ones describing the strong force and the Higgs field, manage their own infinities through a technique called renormalization, absorbing them into a handful of measured constants and moving on. Apply the same trick to gravity, and it fails completely. The infinities keep multiplying instead of canceling, a clear signal that the framework has been pushed somewhere it was never built to go. This exact kind of breakdown, two well-tested frameworks refusing to agree at an extreme, won't be the last one in this story either. It happens again, in a completely different way, at the opposite end of size entirely. In 1955, the physicist John Wheeler gave a name to what might be happening down there. He called it quantum foam, a picture of space-time at the Planck scale boiling with constant, violent fluctuation, tiny wormholes and bubbles winking in and out of existence faster than anything could ever observe them directly. It's a vivid image, and it's worth being honest about what it actually is. Nobody has measured quantum foam. Nobody has confirmed it exists in anything like the form Wheeler pictured. It remains one possible consequence of taking quantum uncertainty seriously at a scale no instrument has ever reached. Different approaches to finishing this part of physics don't even agree on what replaces smooth space once you zoom in far enough. String theory proposes that what look like point particles are actually tiny vibrating loops, with extra spatial dimensions curled up too small to detect at any larger scale, some of them estimated to be wound up at a size close to the Planck length itself. Loop quantum gravity proposes something almost opposite, that space itself is built from discrete chunks, countable and finite, the way matter turned out to be built from atoms rather than being infinitely smooth. A third approach, causal dynamical triangulation, tries to build space-time back up out of tiny simulated building blocks and see what large-scale shape falls out on its own. All three produce a Planck-scale floor. None of them have been tested directly, and they don't agree with each other about what that floor is actually made of. What's genuinely settled is narrower than either picture. We know the combination of constants that produces this length. We know that applying our current equations below it generates nonsense. We know some new description of space and time has to take over at or before this scale, because the old one demonstrably breaks. What we don't know is whether space is smooth all the way down and merely impossible to probe, or genuinely granular, built from some smallest real unit the way matter is built from atoms. That distinction hasn't been settled by experiment, and it may not be settled for a long time. Nobody can reach the Planck scale directly with a particle accelerator, but a few experiments have tried to catch a faint shadow of it indirectly instead. Some quantum gravity models predict that light of different colors, traveling across billions of light years from a distant gamma-ray burst, should arrive at very slightly different times, a tiny dispersion caused by granular space itself acting unevenly on different wavelengths. Telescopes built to catch exactly that effect have been watching for years. So far, the timing has come back clean in every case, which doesn't rule the idea out, but does rule out the most aggressive versions of it. The floor is still standing. It's just gotten harder to imagine it being as rough as some models predicted. Whatever the real answer turns out to be, it sits underneath every atom you're made of, whether or not anyone has ever measured it directly. The quarks inside your body's protons, the gluon field holding them together, the electrons orbiting outside, all of it eventually bottoms out at this same unresolved floor, the same one sitting underneath every atom in the room around you, in the planet under that room, in every star visible from it. It's strange to spend this long building toward an answer and arrive at an honest admission that nobody fully knows, but that's the actual state of the floor beneath measurement itself. Having hit a floor like that, with nowhere left to go downward, there's only one direction left to take this. Out, past atoms, past the solar system most people already underestimate the size of, toward distances built from addition instead of division, where the obstacle stops being a lack of equipment and starts being the sheer scale of ordinary space nobody bothers to picture accurately. What does the nearest star actually look like once the scale stops shrinking and starts growing instead? The nearest star is the Sun. Most people forget that, since it doesn't look anything like the pinpricks scattered across a night sky. But it qualifies in every technical sense, and it's the one star whose true distance almost nobody pictures correctly. The Earth orbits it at an average distance of about 149,600,000 kilometers, a span astronomers shorthand as 1 astronomical unit. Put another way, the distance between Earth and the Sun is roughly 108 times the width of the Sun itself, a single body so large that lining 108 of them edge to edge would only just bridge the gap to the planet orbiting it. Shrink the whole system down to something you could hold, and the distortion in most textbook diagrams becomes obvious immediately. Make the Sun the size of a basketball, about 24 centimeters across, and Earth becomes a single peppercorn, sitting roughly 26 meters away, about the length of 2.5 school buses parked end to end. Neptune, the most distant true planet, ends up more than 3/4 of a kilometer out, the length of about 7 football fields laid in a row. No page, no screen, no classroom poster has room for that. Every diagram you've ever seen of the solar system had to choose between showing the planets at a size you could actually see or spacing them at a distance that was honest, and every one of them chose size because a diagram with 8 invisible dots scattered across a stadium isn't useful for teaching anyone anything. A few places have tried building it at honest scale anyway. The largest is in Sweden, where the Sun is represented by a spherical arena in Stockholm 110 meters across, and the planets are scattered outward from there at the correct proportional distance, full-size models bolted to buildings and roundabouts across the country. Mercury and Venus sit a short walk from the Sun. Jupiter sits at the International Airport outside the city. Pluto, demoted from planet status but kept in the model anyway, sits in a small town nearly 300 kilometers north, the only way to represent its true distance, without the whole project becoming physically impossible to visit in a single afternoon. None of that compression changes what the actual gap is made of, though. Light crosses the distance between the Sun and Earth in about 8 minutes and 20 seconds, moving at the fastest speed anything in the universe is permitted to travel. That isn't a long time by most standards, but it isn't nothing either. And for a long time, nobody knew light took any time at all to get anywhere. That same light, moving at the exact same fixed speed, needs anywhere from about 3 to 22 minutes to reach Mars, depending on where the 2 planets happen to sit in their orbits that month. It needs around 43 minutes on average to reach Jupiter. By the time it reaches Neptune, the edge of the planets most people think of as the boundary of the solar system, more than 4 hours have passed. One continuous beam, never slowing down for an instant, simply covering a distance too large for the trip to feel quick. That changed in 1676 because of a moon orbiting a different planet entirely. The Danish astronomer Ole Romer had been tracking Io, one of Jupiter's 4 largest moons, timing its eclipses as it passed behind the giant planet on a cycle regular enough to set a clock by about every 42.5 hours. The eclipses should have arrived exactly on schedule every single time. They didn't. When Earth was moving away from Jupiter in its orbit, the eclipses ran late. When Earth was moving toward Jupiter, they ran early, by minutes that grew or shrank depending on how the distance between the 2 planets was changing that month. Most astronomers at the time assumed light traveled instantly, arriving everywhere at once with no delay to measure. Rumor worked out that the timing only made sense if light took real, measurable time to cross real distance, arriving later when Earth had drifted farther from Jupiter and earlier when it had drifted closer. He used the discrepancy to estimate roughly how fast light had to be moving. His first number came out lower than the true value, since the size of the solar system itself wasn't yet known precisely enough to nail it down exactly. But the discovery itself was correct, and it was the first real evidence that light had a speed at all, rather than simply existing everywhere instantly. A few years later, the physicist Christian Huygens used Romer's data to calculate an actual number for that speed, the first serious estimate in history. The number kept getting sharper after that. James Bradley refined it in 1729. Watching how starlight appeared to shift angle slightly because Earth itself was moving while the light crossed the telescope, an effect that only makes sense if light arrives at a fixed, finite speed. In 1849, Hippolyte Fizeau measured it without leaving the ground at all, bouncing a beam between two hilltops in France through a spinning toothed wheel and timing how fast the wheel had to turn to block the returning light. Each measurement closed the gap a little further. Today, the value isn't measured at all anymore. It's defined exactly: 299,792,458 meters per second, fixed by international agreement since 1983, with the meter itself now built around that number instead of the other way around. Apply that same 8 minutes and 20 seconds to your own skin, and the sunlight landing on it isn't actually current. It's a small, steady delay, the same one Romer caught hiding in a moon's eclipse schedule 3.5 centuries ago, now arriving as warmth on your arm instead of a discrepancy in a notebook. If the sun vanished completely this instant, gone without a trace, you would keep feeling that warmth. Keep seeing it sitting exactly where it's always been. For the entire 8 minutes and 20 seconds, it would take the news to catch up with you. Gravity would hold on for exactly as long. General relativity predicts that gravitational influence propagates at the same speed light does, no faster, a prediction confirmed directly when detectors finally caught gravitational waves arriving from colliding objects in 2015. Earth would keep its orbit, undisturbed, for those same 8 minutes, circling a sun that technically wasn't there anymore. It's an odd thing to realize that the nearest star in the universe, the one keeping you warm tonight, is something you've never actually seen as it currently is, not once, not for a single second of your life. Even our most ambitious attempt to physically leave the solar system hasn't escaped its outskirts by much. Voyager 1, launched in 1977, has been racing outward for nearly 5 decades now, at about 17 kilometers every second, faster than almost anything else humans have ever built. It only crossed into true interstellar space in 2012, after 35 years of continuous travel. Even now, a radio signal from Earth needs more than 22 hours just to catch up with it, one way. The fastest, farthest traveling object humanity has ever built is still, by the measure the rest of this story is about to use, barely outside the front porch. If even the nearest possible star comes with an 8-minute delay built into it, and our fastest spacecraft still hasn't cleared the porch after 50 years, the rest of the night sky raises a much larger question. What exactly are you looking at when you look up at everything farther out than that? A light year measures distance, not time, even though the name suggests otherwise. It's simply how far light travels in 1 year, moving at that fixed speed locked into the definition of the meter itself, which works out to about 9.5 trillion kilometers. Say a star sits 8 light years away and you're describing a distance, the same way you'd describe a destination in miles rather than the hours it takes to drive there. The confusion only creeps in once you realize that distance and delay are the same fact looked at from 2 directions, since the only way light covers that distance is by spending that much time doing it. A single light year is already harder to hold on to than the light minutes from a few minutes ago. It equals roughly 63,000 astronomical units, the same unit that measured the gap between Earth and the Sun, Sirius, at 8.5 light years, sits more than 500,000 times farther from Earth than the Sun does. The jump from minutes to years isn't a small step up. It's a completely different unit of scale, wearing a deceptively similar name. Picture every point of light in tonight's sky as a letter, mailed from its source the moment it left, traveling at a fixed, unbeatable speed toward your exact location, with no way to arrive any sooner no matter how urgent the news. Some of those letters were mailed recently. Some were mailed before recorded history began. All of them are landing in your mailbox on the same night, regardless of how long ago each one was sent, because each letter only cares about the moment it arrives, never about what else happens to be arriving alongside it. The sky isn't showing you one single moment. It's showing you a pile of unrelated mailing dates that happen to share a delivery day. Sirius, the brightest star in the night sky, sent its letter about 8.5 years ago. Vega sent its about 25 years back. Polaris, the star sitting almost directly above the North Pole, sent its letter roughly 433 years ago, before the telescope had even been invented. Deneb, one of the farthest stars still visible without any equipment at all, sent its letter somewhere between 1 and 2,000 years ago, depending on which distance estimate you trust, meaning the light landing in your eye tonight left before certain ancient empires had finished rising and falling. All 4 of those letters arrived together, every clear night, stacked invisibly on top of each other, with nothing in their appearance hinting at how differently old each one actually is. Brightness in the sky isn't a reliable guide to any of this either. Polaris appears only modestly bright, despite sitting 433 light-years away, because it happens to be a true giant, thousands of times more luminous than the Sun, while plenty of ordinary stars sitting far closer to Earth are too faint to see with the naked eye at all. A point of light's apparent brightness mixes 2 completely different facts together: how much energy the source is actually producing and how far that energy has had to travel to reach you, with no obvious way to separate the two just by looking. A star with enough mass burns through its fuel quickly, sometimes in only a few million years, far less time than light needs to finish crossing a genuinely large distance. For some of the more distant points of light in tonight's sky, it's entirely possible that the source itself no longer exists at all, having already ended in whatever way a star that size ends, while its last several centuries of ordinary light are still quietly completing the commute toward your eyes. None of this would mean anything if we couldn't actually measure how far each letter traveled, and the first reliable method for doing that came from something you can demonstrate yourself, holding up a finger and closing one eye at a time. Close your left eye and your finger appears to shift position against the background. That shift is parallax, and astronomers use the same effect on a much larger baseline, observing a nearby star from opposite sides of Earth's orbit around the Sun, 6 months apart, and measuring the tiny apparent shift against more distant background stars behind it. Friedrich Bessel was the first to pull it off successfully. In 1838, measuring the distance to a faint star called 61 Cygni, using an angle so small it had defeated every attempt before his. The baseline astronomers use is the full width of Earth's orbit, about 300 million kilometers, and the resulting shift for even the nearest stars is smaller than the width of a coin held many kilometers away, which is part of why it defeated so many earlier attempts. Out of that same measurement comes another unit you'll hear sometimes alongside the light year, the parsec, defined as the distance at which a star would show a parallax shift of exactly 1 arc-second against that baseline, a little over 3 light-years per parsec. Different community, same underlying method, just a different way of writing the answer down. Bessel's original measurement was done entirely by eye, through a telescope, with nothing but careful repetition to fight down the uncertainty. Modern versions of the same idea now run from orbit instead. A European satellite called Gaia, launched in 2013, has measured parallax distances for more than 1 billion individual stars, with precision fine enough to catch a shift smaller than the apparent width of a human hair seen from several kilometers away. The principle Bessel proved by hand in 1838 is still the exact principle running the most precise stellar map ever built. There's a deeper problem hiding underneath all of this, one that has nothing to do with how good our instruments get. Once light takes real time to cross real distance, the idea of a single shared present moment stretching across the whole universe stops holding together. Two flashes of light, both reaching you at exactly the same instant tonight, might have left their sources at genuinely different times, depending on how far away each source actually is. Someone moving fast enough in a different direction could watch those same two flashes and judge that one of them arrived slightly before the other instead, and neither observer would be wrong. There isn't one universal present moment that everything is quietly sharing. There's only ever the moment light happens to reach wherever you're standing. This isn't just a thought experiment for astronomers either. When a telescope catches a supernova erupting in a distant galaxy, it's recording the tail end of an explosion that may have actually finished thousands or millions of years earlier. Entire fields of astronomy run on this delay as a working tool rather than an inconvenience, treating distant objects as a kind of archive, each one showing an earlier chapter the farther out you look, with no way to check in on the current chapter until its own light eventually arrives, sometimes long after anyone watching tonight would be around to see it. It's strange to think that the sky has never once shown you a single coherent moment, only an accidental stack of much older ones, arriving together by coincidence rather than by design. With distance turning out to mean the past, every time, no exceptions, one question becomes unavoidable for the rest of this story. What does our actual nearest neighbor beyond the solar system look like once its light gets correctly placed back in the year it actually left? Proxima Centauri sits about 4¼ light-years away, which makes the light reaching Earth from it tonight only about 4 years old, recent by the standards of everything covered so far. That single fact makes it the closest star to the Sun in the entire universe, and the number is still almost impossible to hold on to. 4¼ light-years works out to roughly 40 trillion kilometers, 25 trillion miles, a distance so far past ordinary intuition that converting it into smaller units doesn't actually make it easier to picture, only longer to say out loud. If Voyager 1, after nearly 5 decades of continuous travel, is still just outside the front porch, Proxima Centauri is the nearest other house on the street, and the street itself turns out to be far longer than most people are ever told. Keep Voyager 1 moving at its current speed of about 17 kilometers a second, pointed directly at Proxima Centauri instead of out toward interstellar space in general, and the trip would take roughly 75,000 years. Not 75 years, 75,000. Longer than the entire span of recorded human history, several times over, just to cross the gap to the single nearest star. Conventional rockets run into a hard wall long before reaching speeds anywhere near what a trip like that would need. Every bit of fuel a spacecraft carries adds weight that has to be accelerated too, including the fuel meant to do the accelerating, and the math behind that trade-off scales brutally rather than smoothly. Doubling a chemical rocket's final speed doesn't double the fuel required. It can multiply it many times over, which is part of why every probe humanity has launched toward the outer solar system has relied on gravity assists, stealing a small amount of speed from a planet's own orbital motion rather than carrying enough fuel to do the entire job alone. Faster spacecraft exist, on paper at least. Parker Solar Probe currently holds the record for the fastest speed any human-built object has ever reached, just under 700,000 kilometers an hour at its closest pass by the Sun. That speed only happens because the Sun's own gravity is pulling it inward on a tight, repeated loop, not because it's actually escaping the solar system in any direction. If something could somehow sustain that same speed in a straight line toward Proxima Centauri instead, the trip would still take somewhere around 6,500 years. New Horizons launched faster than Voyager 1 initially, leaving Earth at over 16 kilometers a second, but it received fewer gravitational boosts along the way and has been gradually losing speed ever since, climbing out of the Sun's gravity well the entire time. Voyager 1, helped along by a precisely timed flyby of Jupiter and Saturn decades ago, remains the fastest object actually headed out of the solar system for good. 3 different spacecraft, 3 different ways of claiming a speed record, and none of them anywhere close to what an actual interstellar crossing would require. Proxima Centauri itself wasn't found until 1915, decades after Alpha Centauri, its brighter neighbor, had already been studied for generations. Robert Innes, working at the Union Observatory in South Africa, noticed a faint, dim star drifting slowly against the background sky near Alpha Centauri's position and recognized the motion as a sign of genuine proximity rather than coincidence. Alpha Centauri A and B, the 2 brighter sun-like stars Innes was already familiar with, orbit each other at a separation that ranges between roughly 11 and 36 astronomical units, swinging closer and farther apart over an 80-year cycle, somewhat like the distance between the Sun and Uranus stretched and compressed over time. Proxima's circles that pair from far outside both of them, faint and distant enough that it stayed hidden for as long as it did. It took until relatively recently, with precise velocity measurements taken decades after the discovery, to confirm that Proxima is genuinely gravitationally bound to the brighter pair at all, orbiting them on a path so wide it takes roughly 500,000 years to complete a single loop. A real project does exist aimed at making this exact crossing faster than chemistry or gravity assists ever could. Announced in 2016, Breakthrough Starshot proposes launching a swarm of postage stamp-sized probes, each attached to a thin, reflective sail, and accelerating them with a ground-based laser array powerful enough to push them to roughly 1/5 of the speed of light within minutes. Pulling that off would require a laser array on the ground, delivering something on the order of 100 gigawatts, focused with extreme precision on a sail only a few meters across as it accelerates away at thousands of times the force of gravity for just a few minutes before coasting the rest of the distance unpowered. Dust grains, harmless at ordinary speeds, would hit a sail moving that fast with the force of a small explosion, and shielding against that risk remains one of the unsolved parts of the proposal. At that target speed, theoretically, the crossing to Proxima Centauri would take about 20 years instead of 75,000. Nothing close to that laser array currently exists. The engineering gap between the proposal and a working version of it remains enormous, and the project itself describes the timeline honestly as decades away at best. Part of what makes the gap to Proxima Centauri feel different from the gap between planets is gravity, not just distance. Inside the solar system, gravity never really lets go, tugging on countless icy bodies all the way out through the Kuiper Belt and into the Oort cloud, a vast, thin shell of debris that current estimates place as far as 100,000 astronomical units from the Sun. That's nearly half the distance to Proxima Centauri itself, meaning the Sun's gravitational reach, however faint, may extend almost halfway across the gap before anything resembling true emptiness takes over. Voyager 1 itself, despite having already crossed into interstellar space, won't reach the inner edge of the Oort cloud for roughly another 500 years, and won't clear its outer edge for closer to 30,000 years after that. Even the most traveled object humanity has ever built remains, in that sense, still inside the Sun's own gravitational neighborhood, with the genuinely empty stretch toward Proxima Centauri still entirely ahead of it. Picture the sun as a single porch light in a stretch of country road with no other lights for as far as anyone has ever measured. Walk that road at any believable human pace and the next porch light, Proxima Centauri, wouldn't appear for longer than civilization itself has existed. It isn't simply far. It's isolated in a way that distance alone doesn't quite capture. The nearest neighbor sitting close enough to name and study in detail, while remaining functionally unreachable by anything currently built. There's something almost humbling about a star this close, still being this unreachable, the nearest possible neighbor turning out to prove the rule rather than break it. If even the single nearest star in the entire universe is isolated on a scale like that, the rest of the night sky raises an odd question of its own. Why do so many stars, scattered across distances this extreme, still look like they're standing right next to each other? The Big Dipper looks like a single coherent shape, 7 stars holding a steady formation against the rest of the sky. The same outline anyone in the northern hemisphere could sketch from memory. None of those 7 stars sit anywhere near each other in actual space. Megrez, the closest of the 7, sits about 58 light-years away. Dubhe, the star at the front edge of the bowl, sits more than twice as far, at roughly 123 light-years. The other 5 fall somewhere in between, scattered across a real depth of more than 60 light-years that the shape itself gives no hint of at all. The actual situation is stranger than a simple illusion, though, because 5 of those 7 stars genuinely are related to each other, just not in the way the shape suggests. Merak, Phecda, Megrez, Alioth, and Mizar share a common origin, born from the same star-forming cluster an estimated 300 million years ago, and still drifting through space together at matching speed and direction, a loose family of siblings called the Ursa Major Moving Group. Dubhe and Alkaid, the 2 stars at the very ends of the shape, the pointer and the tail, aren't part of that family at all. They're unrelated stars, moving in completely different directions that simply happen to line up with the other 5 when viewed from exactly where Earth sits right now. Mizar, one of the 5 true siblings, turns out to be hiding an additional twist of its own. Look at it through even a modest telescope and it splits into 2 separate stars, Mizar and Alcor, a pairing visible to sharp naked eyes that ancient observers reportedly used as an informal eyesight test. Giovanni Battista Riccioli examined it through a telescope in 1650 and found that Mizar itself wasn't a single point either, becoming the first double star ever confirmed with an instrument. Modern spectroscopy went further still. Mizar A and Mizar B each turned out to be a tight pair of stars orbiting too closely to separate visually, and Alcor carries a faint companion of its own as well. What looks like one ordinary point of light in the handle of the Dipper is, by the most careful modern count, 6 separate stars occupying what appears from Earth to be a single position. That alignment isn't permanent. The 5 true siblings and the 2 unrelated interlopers are all drifting at their own pace and in their own direction, and the shape itself is slowly coming apart as a result. 100,000 years ago, the Big Dipper didn't look like a dipper at all. The same 7 stars scattered into an unfamiliar arrangement. 100,000 years from now, it won't look like one either. Most of that distortion comes down to the 2 outsiders pulling away from the group's shared motion. The bowl will stretch as Dubhe drifts off on its own path, and the handle will bend in a different direction as Alkaid does the same, gradually unfolding a shape that took a few 100,000 years to assemble by coincidence and will take about as long to fall back apart. The shape everyone recognizes is a brief, accidental alignment, true for perhaps a few 100,000 years out of a universe that's been running for 14 billion. None of this is unique to one constellation either. Most of the patterns visible in the night sky mix at least a few genuinely related stars with several complete strangers, lined up by coincidence rather than by birth, with the Big Dipper simply happening to be a clean, well-studied example of a pattern playing out almost everywhere you look. None of this depth shows up to the naked eye for a simple geometric reason. Stand at one point and look outward in roughly the same direction, and every object along that direction lands on the same patch of sky, regardless of how far back it actually sits, the same way a nearby lamppost and a distant mountain can appear to touch each other from exactly the right angle, despite being separated by miles. The eye has no built-in sense of depth at distances this extreme. Even parallax, the method that finally let astronomers measure these distances accurately, only works because of a careful, deliberate comparison across opposite sides of Earth's orbit. Look up on any ordinary night, and that comparison never happens. Every star just lands on the same flat dome, sorted only by direction, with distance quietly erased from the picture. Parallax works cleanly for relatively nearby stars like these 7, all close enough for the shift to stay measurable with precision. Stars much farther out require a different trick, comparing a star's color and spectrum against others of known type and known distance, then inferring how far away it must actually sit to produce the brightness observed from here, a method astronomers call spectroscopic distance estimation. It's less direct than parallax, built on comparison rather than pure geometry, but it extends the reach of stellar mapping far past where the tiny shift Bessel first measured would ever stay detectable. Brightness doesn't rescue the missing depth either, and it can actively work against you. 2 stars sitting at wildly different true distances can still appear almost equally bright from Earth, if the farther one happens to be intrinsically far more luminous than the nearer one, burning hotter or larger and simply overpowering the disadvantage of extra distance. A red giant, nearing the end of its life, can output thousands of times more energy than an ordinary stable star like the Sun, simply by swelling to an enormous size late in its life. Place that giant several times farther away than a smaller, ordinary star, and the two can still arrive at your eye carrying nearly identical brightness, the giant's sheer output making up for the extra distance it has to cross. Nothing about the dot of light itself, its color, or its twinkle, or its position inside a familiar shape, gives away which kind of star you're actually looking at. So the honest answer is that a constellation is mostly an angle, not a location. It's a record of which direction 7 points of light happen to share from one specific vantage point at one specific moment in cosmic time, with almost no information about how far back each point actually sits. The shape feels solid because human vision was never built to notice the difference between near and far at distances like these, only to notice where something sits against everything around it. If the patterns scattered across the sky are mostly accidents of viewing angle, with real distance hidden behind every one of them, the next honest question is what the actual structure looks like once that flattening trick gets undone completely. What does the galaxy actually look like once you stop trusting the shapes it seems to make? William Herschel tried to answer that exact question in 1785, using nothing more sophisticated than a telescope and a count. Herschel didn't simply use whatever instrument was already available either. He built his own telescopes, including some of the largest in the world at the time, with his sister Caroline Herschel working alongside him as a full astronomical collaborator, grinding mirrors, recording data, and independently discovering several comets of her own in the process. His method, now called star gauging, involved pointing one of those telescopes in hundreds of different directions across the sky and simply counting how many stars showed up in each one, working on the assumption that stars were scattered through space at roughly the same density everywhere, and that running out of visible stars in a given direction meant you'd finally reach the true edge of the system in that direction. Count carefully enough, in enough directions, and the resulting shape should reveal the galaxy's outline from the inside, The same way counting how far you can throw a sound in different directions inside a room could, in theory, sketch out the room's walls. Herschel's count produced a shape, a flattened, lens-like disk of stars, wider than it was thick, which was a genuinely good description of the Milky Way's actual structure. Where Herschel went wrong was in placing the Sun almost exactly at the center of that disk, since his star counts came out roughly symmetric in every direction, thinning out at about the same rate no matter which way he pointed the telescope. Symmetric thinning looked exactly like what you'd expect from sitting at the middle of things. The space between stars and the galactic disk isn't perfectly clear. It's threaded with thin clouds of dust and gas, invisible to the naked eye but dense enough over thousands of light years to dim and redden starlight passing through it. Herschel had no way to know that dust, not distance, was cutting his view short in every direction at roughly the same rate, creating a false symmetry that looked exactly like sitting at the center of a system you were actually sitting well off to one side of. The tool that finally cut through the problem came from an unrelated discovery. Henrietta Swan Leavitt worked at the Harvard College Observatory, one of several women hired at the time to analyze photographic plates by hand for a fraction of what male astronomers were paid, in a role the observatory called a computer. Studying thousands of variable stars within the Magellanic Clouds, two small companion galaxies where every star sat at roughly the same distance from Earth, she could compare their brightness directly against each other without distance getting in the way. In 1908, she found that each star's pulsing period was directly tied to its true luminosity. Brighter stars pulsing more slowly, fainter ones more quickly, a relationship precise enough to use as a genuine measuring tool. Once you knew a star's pulse rate, you knew its real brightness, and comparing real brightness against apparent brightness from Earth gave you distance far beyond anywhere parallax could ever reach. Harlow Shapley picked up that tool in 1918 and pointed it somewhere. Herschel never could have, at globular clusters, dense, ancient balls of hundreds of thousands of stars that sit above and below the dusty disk entirely, clear of the obstruction that had fooled every star count made from inside the disk itself. Mapping their true three-dimensional positions using Leavitt's relationship, Shapley found that the clusters weren't scattered randomly or centered anywhere near the Sun. They formed a roughly spherical halo, centered on a point tens of thousands of light years away, in the direction of the constellation Sagittarius. The Sun wasn't anywhere close to the middle of anything. It was sitting far out toward the edge of an enormous structure whose true center had been hiding behind dust the entire time. Shapley's own first estimate of the Milky Way's total size came out too large, by roughly a factor of 2 or 3, since he hadn't yet fully corrected for the same dimming dust that had misled Herschel more than a century earlier. The center of the picture was right. The exact scale needed a few more decades of refinement to settle down to the numbers used today. The modern figure puts the Sun at roughly 26,000 light-years from the actual galactic center, embedded in a relatively minor structure called the Orion Arm, sometimes described as a spur rather than a full spiral arm, wedged between two larger arms named for Sagittarius and Perseus. Far from sitting at the center of a tidy, symmetric system, the solar system occupies a modest, slightly out-of-the-way position in one of several spiral arms winding around a galactic core most of us will never see directly with our own eyes. Mapping the spiral structure itself eventually required getting around the same dust problem Herschel never knew he had. Visible light still struggles to cross the galactic disk over large distances, but radio waves pass through the same dust far more easily. The specific signal that made this possible is a faint radio emission at a wavelength of 21 centimeters, produced when the lone electron inside a hydrogen atom flips its magnetic orientation, a transition so rare for any single atom that it might happen only once every several million years, but reliable enough across the enormous quantities of hydrogen gas filling the galaxy to add up to a clear, mappable signal. Hendrik van de Hulst predicted that signal theoretically in 1944, and Harold Ewan and Edward Purcell detected it directly in 1951, finally giving astronomers a way to trace the galaxy's gas, and by extension its spiral structure, straight through dust that visible light could never cross. All of this structure is also in motion. The Sun, along with everything else in the Orion Arm, orbits the galactic center at roughly 220 kilometers a second, completing one full circuit in approximately 230 million years, a span sometimes called a galactic year. That same orbit isn't perfectly flat either. The Sun drifts gently above and below the plane of the galactic disk as it travels, completing one full up and down cycle roughly every 30 to 70 million years, weaving through the same disk it's also circling, a slow vertical rhythm layered on top of the much larger orbital one. The solar system has completed perhaps 20 of those great orbits since it formed, circling a center none of us have ever seen, at a position nobody suspected until barely a century ago. It's a strange kind of demotion, finding out that the system holding everything you know isn't special even by its own galaxy's standards, just one ordinary spur among several, partway around one ordinary orbit among many. If the Milky Way isn't centered on anything familiar, and the Sun turned out to be an ordinary resident rather than a central one, the next question is even less settled. Where does the Milky Way itself actually end? And how would anyone sitting inside it ever know for certain? For most of history, that question tangled up with a completely different one. Scattered across the night sky are faint, fuzzy smudges of light, visible without a telescope in only a handful of places, that early astronomers lumped together under a single vague label, nebulae, without any real way to know what they actually were. Some clearly sat within our own galaxy, glowing clouds of gas lit up by young stars forming inside them. Others might have been something else entirely, and for a long time nobody had a way to tell the difference. In 1755, the philosopher Immanuel Kant proposed an answer based on nothing but careful reasoning by analogy, decades before any telescope could test it directly. Our own galaxy, seen from inside it, appears as a faint band of light stretching across the sky, the edge-on view of a flattened disk. Kant suggested that if some of those unresolved nebulae showed a similarly faint, elongated shape, they might not be clouds inside our own system at all. They might be entire separate disks of stars, full galaxies in their own right, simply too far away to resolve into anything but a smear of light, the same way our own galaxy would look to an observer standing impossibly far outside it. He called them island universes, and the idea remained pure speculation for more than a century, with no instrument anywhere near capable of confirming it. That same book held another, equally significant guess sitting right alongside it. Kant proposed that solar systems themselves form from a slowly collapsing, rotating cloud of gas and dust, flattening into a disk as it contracts, a basic picture modern astronomy still uses essentially unchanged to explain how stars and planets actually form. He'd guessed at the architecture of both the very large and the very small in the same single book, decades before either idea could be tested by anyone. William Herschel, already deep into the star-gauging project covered a few minutes ago, ran into the same nebulae constantly and started cataloging them by the thousands. His son, John Herschel, carried the project even further, traveling to South Africa specifically to catalog the nebulae visible only from the southern hemisphere, ones his father could never have observed from England. Their combined work eventually grew into a catalog of nearly 5,000 entries, later reorganized by John Lewis Emil Dreyer into what's still called the New General Catalog today. Andromeda's other common name, NGC, 224, comes directly from that 19th century list, still in active use by every astronomer working with it now. A clear pattern emerged as telescopes improved across that whole project. Some nebulae, pushed under enough magnification, dissolved into countless individual pinpoints of light, revealing themselves as dense star clusters rather than clouds at all. Others refused to resolve no matter how much power was thrown at them, staying smooth and diffuse under every telescope available, behaving exactly like what they actually were, genuine clouds of gas with no individual stars to find. Two completely different kinds of object were hiding under one shared, vague label, and there was no way yet to tell which kind any particular smudge belonged to just by looking. The next real step came from the largest telescope in the world at the time, built by William Parsons, the 3rd Earl of Ross, on his estate in Ireland, and completed in 1845. Astronomers nicknamed it the Leviathan of Parsonstown for its sheer size, a 72-inch mirror gathering more light than anything built before it. Building it took years and required constructing massive stone support walls just to hold the telescope's tube steady, since nothing of that scale had ever been attempted before. It held the record as the largest telescope in the world for more than 70 years, not surpassed until a new telescope arrived in California decades later. Pointed at a particular nebula in the constellation Canes Venatici, it resolved something no smaller telescope ever had: a clear spiral structure, distinct curling arms wound around a bright center, far more organized than a simple gas cloud had any reason to be. It still couldn't resolve individual stars within that spiral. It could only prove the shape was too structured to dismiss as ordinary gas, raising the stakes on Kant's old guess without settling it. By the start of the 20th century, astronomers had catalogued thousands of these spiral-shaped nebulae scattered across the sky, far too many to dismiss as a handful of unusual local objects. If even a fraction of them turned out to be separate galaxies rather than clouds within our own, the basic scale of the universe would need a complete rewrite. The question stopped being a quiet philosophical curiosity and became one of the most urgent open problems in astronomy. Settling it required another 70 years and an even larger telescope, the 100-inch Hooker telescope at Mount Wilson in California, completed in 1917, and still the largest in the world, when an astronomer there turned it toward the nebula in the constellation Andromeda in the early 1920s. For the first time, individual points of light resolved out of what had always looked like a single smooth smudge, unmistakably separate stars rather than glowing gas. A genuine cloud cannot do that under any amount of magnification, since there's nothing point-like hiding inside it to resolve. Stars can, and now they finally had. Among those newly resolved points was a single star whose brightness rose and fell on a steady cycle. The exact signature Henrietta Swan-Leavitt's relationship from a few minutes ago could convert directly into distance. The number that came back ended the argument completely. Andromeda sat roughly 2.5 million light-years away, far beyond any boundary the Milky Way could plausibly claim, containing on the order of 1 trillion stars of its own, a separate galaxy in every meaningful sense. It turned out to be not just comparable to the Milky Way, but larger by most estimates. A genuine twin system rather than a smaller companion, every bit as real and as large a structure as the one holding the Sun. Kant's reasoning from 1755, built entirely on analogy with no way to check it, turned out to be correct, confirmed 169 years after he first wrote it down. If a single galaxy took this much work just to correctly identify as one object rather than a local cloud, the next layer of structure raises an even harder version of the same problem. What actually holds an entire cluster of separate galaxies together once you have more than one of these enormous systems to account for at the same time? Galaxy clusters move as though something is holding them together that no telescope has ever managed to see directly. The galaxies inside a typical cluster orbit each other fast, fast enough that the combined gravity of every star and every cloud of gas visible within the cluster isn't nearly enough to keep them bound together at all. By the math alone, clusters like this should be flying apart, their galaxies scattering off in every direction within a few 100 million years. They aren't. Something else is providing the gravitational grip holding the whole structure intact, and that something refuses to show up in any photograph. Fritz Zwicky noticed the discrepancy first. In 1933, studying a cluster of galaxies in the constellation Coma Berenices. Using the redshift of each galaxy's light to measure how fast it was moving relative to the others, he calculated the total mass the cluster would need to gravitationally hold those velocities together, then compared that figure against the mass of all the visible, light-emitting matter the cluster actually contained. The math behind that calculation, called the virial theorem, relates how fast objects in a gravitationally bound system move to how much total mass must be holding them together, the same basic logic used to estimate a planet's mass from how quickly something orbits it. The numbers didn't come close to matching. Zwicky's calculation suggested the cluster needed hundreds of times more mass than anything visible could account for, and he gave the missing portion a name that's stuck ever since: dark matter, matter that exerts gravity, but produces no light of its own to give its presence away. Zwicky himself wasn't an easy person for the rest of the field to embrace. He was known for blunt, often abrasive criticism of other astronomers, and much of his work got quietly set aside for decades rather than seriously investigated, more because of how unwelcome he made himself than because of any specific flaw in the data. He was right about more than dark matter, too. A year earlier, working with Walter Bade, he had correctly predicted the existence of neutron stars and proposed that supernovae were the violent process that created them, years before either idea could be confirmed. Being right twice in the early 1930s didn't buy him much patience from a community that mostly preferred not to deal with him directly. The discrepancy he'd found sat largely ignored until Vera Rubin picked up a related thread in the 1970s, working with the astronomer Kent Ford on something more specific than cluster-wide motion: the rotation of individual spiral galaxies. Stars orbiting near the visible edge of a galaxy should move slower than stars orbiting closer to the dense, bright center, the same way planets farther from the Sun orbit more slowly than planets closer in. Rubin and Ford measured the actual orbital speeds across dozens of spiral galaxies, starting with Andromeda itself, and found something that flatly contradicted the expectation. Stars far out at the visible edge were moving just as fast as stars much closer to the center, sometimes faster, a pattern that should be physically impossible unless a great deal of additional, invisible mass was spread out through the galaxy's outer regions, well past where the visible stars thinned out to almost nothing. By the early 1980s, Rubin and Ford had measured the same flat rotation pattern across more than 60 spiral galaxies, turning what could have been one unusual case into an unmistakable, repeating rule. Rubin's measurements are now considered some of the most consequential observational evidence in modern astrophysics, though she never received a Nobel Prize for the work before her death in 2016, an omission many in the field still consider a significant oversight. Both discoveries work the same basic way: inferring something you can't see from how it's pushing on something you can. Picture trying to estimate the size of a hidden crowd, not by counting heads, but by how hard the bleachers sway underneath them. The motion gives away a presence the eye alone never would have caught. Galaxies and clusters sway under gravity exactly the same way, revealing mass through motion that no photograph, however long the exposure, ever directly shows. There's a direct echo here to a field discussed earlier in this story, the one giving fundamental particles their mass. That field was never seen directly either, only inferred first through its effects and eventually confirmed by catching its smallest possible ripple. Dark matter sits in roughly the same epistemic position today, decades on, known confidently through its gravitational effects, still without anyone having caught the thing itself directly, just at a scale large enough to hold entire galaxies together instead of small enough to hide inside a single proton. One of the strongest pieces of evidence that this missing mass is genuinely a separate substance, not simply ordinary matter too dim to see, came from watching two galaxy clusters collide. Astronomers studying a system nicknamed the Bullet Cluster, using observations from an orbiting X-ray telescope alongside gravitational lensing measurements published in 2006 by Douglas Clow and his team, found that the visible, light-emitting gas from both clusters had collided, slowed down, and piled up in the middle, exactly the way two clouds of ordinary matter should behave on impact. Gravitational lensing maps, built from how the collision bent the light of objects behind it, showed the bulk of the actual mass had sailed straight through the collision instead, barely interacting at all, landing well ahead of the visible gas on both sides. Whatever makes up most of the mass in that system passed through itself without slowing down, behaving nothing like the ordinary matter sitting tangled up in the middle. By the most recent measurements, dark matter outweighs ordinary visible matter by roughly 5-to-1 across the universe as a whole, the overwhelming majority of everything with mass refusing to interact with light at all. What it's actually made of remains genuinely unresolved. Several candidate particles have been proposed, heavy, weakly interacting particles nicknamed WIMPs among the most popular, along with a much lighter hypothetical particle called the axion. Detectors built deep underground, shielded from ordinary cosmic radiation by thousands of feet of solid rock, have spent years waiting for one of these candidates to occasionally bump into a normal atom and leave a detectable trace. So far, none of them have caught a confirmed signal, narrowing down what dark matter could be without yet revealing what it actually is. It's an odd kind of trust, building an entire picture of the universe's structure on something nobody has ever actually seen. If a single cluster needs this much invisible scaffolding just to hold its galaxies together, the next layer of structure raises the same problem at a scale roughly 1,000 times larger. What does it take to hold an entire collection of clusters together, once clusters themselves turn out to be the smaller piece? The Milky Way and Andromeda, the two largest systems we've built up to in this story so far, aren't alone. They're part of a collection of roughly 54 gravitationally bound galaxies called the Local Group, spread across a region about 10 million light-years wide. Most of the members are small, dim satellite galaxies, clinging to either the Milky Way or Andromeda, like moons around a planet, too faint to see without a telescope, and too small to make much gravitational difference to the overall structure. The two giants dominate the group's mass almost entirely, everything else a kind of scattered footnote. What makes the Local Group feel like a coherent object is gravity. The mutual pull between every member slowly shaping their orbits, pulling Andromeda toward the Milky Way at over 100 kilometers a second, despite the distance separating them, a closing that will end in a genuine merger somewhere around 4.5 billion years from now. Now here is where the scale starts to feel strange. The Local Group, which contains two enormous galaxies and dozens of smaller ones, which spans 10 million light-years and contains hundreds of billions of stars, is itself just a minor outlying member of something considerably larger. Roughly 50 million light-years away from us in the direction of the constellation Virgo sits a dense, sprawling collection of at least 1,300 galaxies, possibly several thousand depending on how far the count extends, clustered tightly enough to exert a measurable gravitational pull on everything in the surrounding region. The galaxies themselves, visible as points and smears of light, account for only a fraction of the cluster's total mass. The bulk of the ordinary matter inside the Virgo cluster isn't locked into stars at all. It fills the space between galaxies as an enormous, diffuse cloud of gas heated to millions of degrees, hot enough to emit X-rays rather than visible light, Detectable only by telescopes, operating at wavelengths the human eye was never built to see. Below that hot gas, both in the visible galaxies and spread throughout the cluster's outer halo, sits dark matter scaffolding that makes up the majority of the total mass in the entire structure, the same invisible component that first showed up in Zwicky's velocity calculations almost a century ago, now operating at a scale more than 1,000 times larger than the cluster he was studying. The local group falls within its gravitational sphere of influence even from 50 million light-years out, slowly drifting toward it at several hundred kilometers a second, pulled along without any single planet in the local group having ever been aware it was moving in that particular direction at all. The Virgo cluster itself is not the top of the hierarchy. It's the dense core of something called the Virgo supercluster, a flattened, irregular structure stretching across roughly 110 million light-years and containing somewhere between 100 and 200 galaxy groups and clusters, depending on where the boundary is drawn. The local group sits at the outer edge of that supercluster, far enough from the core that the pull from Virgo's center is weak here, barely enough to keep us falling inward. In fact, the expansion of the universe is actually winning this particular contest. Cosmological expansion is carrying the local group away from the Virgo cluster faster than the cluster's gravity can reel it back in, which means we are, right now, on the wrong side of an invisible dividing line, close enough to feel Virgo's pull slowing our expansion slightly, but too far out to ever actually fall in. We will never arrive at the center of the structure we've belonged to for billions of years. What the gravitational accounting reveals, when you try to hold all of it at once, is something that has almost no human-scale equivalent to compare it to. Rain falls on a hillside, flows into streams, streams merge into rivers. Rivers carry everything into the ocean without any individual drop knowing about the watershed it belongs to. Superclusters work on roughly the same organizational logic, with smaller groups and clusters feeding gravitationally into a shared central structure, except that the watershed here spans 100 million light-years. The streams are made of galaxies instead of water, and nothing moving through this system is aware it is part of any larger flow. There's no surface to touch, no boundary to cross, no visible edge to find. The structure is entirely real and entirely invisible as a structure, detectable only by mapping the velocities of everything inside it and asking what mass distribution could be causing them. Until 2014, most astronomers treated the Virgo supercluster as the right way to describe the structure we belong to. Then, a paper by Brent Tully, Hélène Courtois, Yehuda Hoffman, and Daniel Pomered published a velocity map of roughly 8,000 galaxies in our region of the universe, carefully measuring how each one was moving and asking what the overall flow pattern implied about the underlying gravitational landscape. What the map revealed was that the Virgo supercluster isn't really a single, self-contained object by any natural gravitational definition. It's one drainage basin feeding into a larger system, along with 4 other superclusters, all of them pouring their motion toward the same distant gravitational center. Tully and his team named this larger structure Laniakea, a Hawaiian word meaning immeasurable heaven. It stretches across roughly 500 million light-years and contains the mass equivalent of roughly 100 million billion suns, about 100,000 galaxies in total, and we sit near one edge of it, far from where the inward flow converges, in the outermost reaches of a supercluster that itself barely qualifies as a tributary to the whole. The center of that flow sits in a part of the sky, our own galaxy's disk blocks from direct observation in visible light, requiring radio and infrared surveys to see through. What's actually pulling hundreds of thousands of galaxies in the same direction isn't one exotic object or one especially dense cluster. It's an ordinary concentration of mass, more galaxies, and more dark matter scaffolding packed into one region than the surrounding area, exerting a pull so gradual and so vast that nothing inside it notices the acceleration any more than you notice the Earth's orbital motion around the Sun. What's deeply strange about all of this is that none of it was known 30 years ago. The concept of the local group has been in use since 1936. The Virgo cluster was catalogued well before that. But the idea that these were nested pieces of something called a supercluster didn't fully develop until the 1980s, and the picture of Laniakea as a single coherent gravitational basin was proposed less than a decade ago and remains actively debated. We've been members of the largest named structure in our observable neighborhood our entire existence as a species, and the structure received its name within living memory. If superclusters this large are real objects, and if they leave gaps between themselves as enormous as their own size, the space in between should be the emptiest thing the universe produces. What actually fills that space, and what does almost nothing look like at this scale? The large-scale structure of the universe, once you step back far enough to see it whole, looks nothing like the inside of a sphere scattered evenly with galaxies. It looks more like a three-dimensional foam, with thin walls and long filaments of matter stretched into vast, interconnected sheets, and enormous, nearly empty bubbles filling all the space in between. Those bubbles are cosmic voids, and they aren't rare. They aren't gaps or anomalies. By volume, they account for roughly 80% of the observable universe. Empty space, organized into enormous connected regions, is the statistical default of what the universe produces when gravity has had 13 billion years to sort matter around. The way voids form is gravity working in reverse from how most people picture it. In the early universe, matter wasn't distributed perfectly evenly. There were slight, random differences in density from one region to another, regions with fractionally more matter and regions with fractionally less. In dense regions, gravity did what gravity always does, pulling surrounding matter inward, building clusters and filaments over billions of years. In the slightly underdense regions, the opposite happened. The matter that was there got pulled outward, toward the denser surrounding structures, leaving behind an emptiness that grew steadily as the dense regions around it pulled harder and harder, and matter streamed away from the inside out. Voids weren't carved out of something solid. They were abandoned, slowly, as their contents migrated toward wherever the pull was slightly stronger. How clearly voids show up depends entirely on how large a survey you run. For most of the 20th century, galaxy surveys were small enough that the voids were hard to trace as a connected network. The picture changed dramatically in the early 2000s when the Sloan Digital Sky Survey began systematically mapping millions of galaxies across a substantial fraction of the sky in 3 dimensions, building the first maps detailed enough to show the cosmic web as a continuous structure. What those maps revealed was that voids aren't scattered randomly or independently. They're organized, fitting together into a connected network of bubbles, their walls shared with neighboring voids, the filaments between them marking the places where 2 or more bubbles press together, concentrating matter into the bright threads visible in any large-scale structure map today. A typical void in the nearby universe spans somewhere between 60 and 300 million light-years across, and the galaxy density inside one runs at roughly 10 to 20% of the cosmic average, not completely empty, but so sparse that a civilization born inside one would be looking out at a very different night sky. Galaxies inside voids do exist, and they've been studied carefully enough to find a consistent pattern in what they look like. Void galaxies tend to be bluer, younger, less massive, and less likely to have been disturbed by close encounters with neighbors, simply because neighbors are rare. They've had the same amount of time as any other galaxy to evolve, but have done it largely alone, without the gravitational harassment from passing companions that shapes galaxies in denser regions, making them a kind of control group for how a galaxy develops when nothing much disturbs it. Its telescopes, assuming the civilization eventually built them, would find galaxies scattered thinly at its edges, far fewer nearby neighbors than any civilization embedded in a filament or cluster would ever see, with the dense cosmic web entirely absent from the interior view. Depending on where exactly inside the void the civilization sat, it might look out and see no significant structure for hundreds of millions of light-years in every direction, the nearest filament of galaxies sitting so far away that early telescopes might not reach it at all. The epistemic consequences of being born in that situation are genuinely strange to think through. A civilization inside a deep void, working with the technology available at its equivalent of our 19th century, would have a night sky thin enough to support a very different cosmological picture than the one humanity arrived at. It might reasonably conclude that the universe was mostly empty, with matter scattered sparsely everywhere, rather than concentrated into a web of structure. It would still see the cosmic microwave background, the faint afterglow of the early universe, since that comes from every direction equally and fills the whole observable sphere, regardless of where the observer sits. But the pattern of nearby structure, the kind of structure that helped us trace the web, might simply be absent from everything that civilization could reach, with instruments built within one lifetime of development. Its picture of the universe would be correct in some ways and quietly missing something enormous, with no way of knowing what it couldn't see. The physics inside a void is the same as the physics anywhere else. Stars form inside voids. Galaxies exist there, just more sparsely. A civilization inside a void wouldn't experience anything obviously different day to day, since nothing about void space pushes or pulls differently than cluster space. The missing information is structural, not physical, a gap in context rather than a difference in local conditions. We are not, as far as anyone can determine with confidence, living inside a true deep void. Our local region of the universe sits inside Laniakea's structure, embedded in a real filament with real neighboring clusters and a real supercluster around us. There is, however, a genuinely contested suggestion in current cosmology that we may sit inside a mild, broad local underdensity, sometimes called the KBC void after the researchers who quantified it most carefully, spanning something in the range of 2 billion light-years across. If that underdensity is real and as significant as some estimates suggest, it may contribute to the disagreement between different methods of measuring how fast the universe is expanding, a tension that turns up later in this story. The underdensity isn't confirmed as a true deep void and isn't confirmed as the cause of the tension, but it's being taken seriously enough by enough people that it appears regularly in the current literature rather than being dismissed. What stays true regardless is that the void is the default. Most of the universe's volume, by a wide margin, is this kind of sparse, abandoned space, slowly growing as matter continues to drain toward the filaments and walls surrounding it. The dense structures we've traced across this story, galaxies, clusters, superclusters, Laniakea itself, are the exception rather than the rule, clustered into a thin, interconnected web that surrounds emptiness far more than it fills it. If emptiness is the default and density the exception, the next question is what shape the exceptions actually take once you map them from outside. The filaments and walls surrounding the voids form a pattern, and that pattern has a shape, and that shape has limits, or should. What happens when a structure appears that pushes against those limits? In the 1980s, a group of 7 astronomers set out to measure how fast a large sample of elliptical galaxies were actually moving through space, not relative to each other, but relative to the overall expansion of the universe itself. Every galaxy in an expanding universe is expected to be receding from every other at a rate that scales with the distance between them, what astronomers call the Hubble flow. The actual velocity of a galaxy adds a second layer on top of that baseline, driven by gravity from the specific structures in its local neighborhood rather than by expansion alone. That extra velocity, The amount by which any given galaxy moves differently from the bare expansion prediction is called its peculiar velocity, and it points in a direction toward whatever is pulling it. The group, later nicknamed the Seven Samurai, published their results between 1987 and 1988. What they found was that a large number of galaxies across our local region of the universe were moving in broadly the same direction, toward a point in the sky around the constellation Centaurus, with peculiar velocities too large to be explained by anything visible in that direction. Something was pulling them, pulling us too, since the Milky Way carries the same peculiar velocity as everything else in the local flow. The group called the source the Great Attractor, and nothing in the data told them what it actually was. The technique the Seven Samurai used requires knowing true distances independently, which brought back the same distance ladder problem that runs through this entire story. Their distance measurements carried uncertainties large enough that the location and mass of whatever was causing the flow remained contested for years after the original paper. Follow-up surveys with larger samples and better calibrated distances progressively narrowed the uncertainty, including a substantial contribution from the Cosmic Flows project led by Brent Tully, the same researcher behind the Laniakea mapping, which assembled a database of galaxy velocities detailed enough to map the flow field across the local universe rather than just detecting an anomaly in it. The problem with looking directly at the Great Attractor isn't the distance. The problem is what's in the way. The Milky Way's own disk, seen edge-on from our position inside it, stretches as a band across the entire sky, dense with dust and gas that blocks, dims, and confuses observations in visible light across a strip covering roughly 20% of the total sky. Astronomers call this region the zone of avoidance. In optical surveys of the universe, it's simply a blind spot, a band of missing data that happens to include the precise region of sky where the Great Attractor sits, making it nearly impossible to inventory the mass hiding behind it using the same tools that mapped everything else in this story. Infrared and radio wavelengths pass through the dust far more easily than visible light, and over the following decades, astronomers used both to push progressively deeper into the zone of avoidance. There's an independent line of evidence pointing in the same direction that doesn't require piercing the zone at all. The cosmic microwave background, the faint afterglow of the early universe that fills the entire sky uniformly, isn't quite uniform in practice. From Earth's perspective, it appears very slightly hotter in the direction of the Great Attractor and very slightly cooler in the opposite direction, a tiny temperature difference caused entirely by our own motion through it, the same Doppler shift that makes an approaching ambulance sound higher-pitched and a receding one lower. Measuring that temperature asymmetry gives the full peculiar velocity vector of the solar system relative to the background radiation itself, confirming independently that something is pulling us in exactly the direction the galaxy velocity maps indicated. What the CMB can't do is say what the source is, any more than the hotter side of a room tells you how large the fire actually is. What they found in 1996, using infrared observations led by Renée Cron-Korteweg and her collaborators, was a remarkably dense galaxy cluster, sitting almost exactly where the velocity map said something large should be, named the Norma cluster and catalogued as Abell 3627. Dense enough and massive enough to account for a meaningful part of the observed flow. Not all of it, because there's something else sitting even further back. About 650 million light-years away, in the same general direction but far beyond the Great Attractor region itself, sits the Shapley supercluster, the most massive concentration of galaxies, within roughly 1 billion light-years of the Milky Way, a system containing hundreds of galaxy clusters and groups packed into an unusually dense volume. Its mass is large enough to contribute its own gravitational pull to the overall flow at our location, layered on top of the Great Attractor's pull, both pointing in roughly the same direction and difficult to disentangle from each other in early velocity maps that couldn't separate their individual contributions cleanly. Current models suggest that both the Norma cluster region and the Shapley supercluster contribute meaningfully to the anomalous flow, neither one the single answer the original discovery seemed to suggest. What's interesting about the Great Attractor story, and what gets lost if you focus only on the mystery, is what it isn't. It isn't one exotic object. It isn't a black hole of unusual size, or a collapsed structure unlike anything else in the universe, or a remnant of something from physics outside the standard picture. It's a concentration of ordinary mass, ordinary galaxies containing ordinary stars containing ordinary atoms, organized into a cluster denser than its surroundings, doing exactly what gravity always does at any scale in this story, pulling everything in the neighborhood toward it. The mystery wasn't the physics. The mystery was the blind spot that prevented us from simply pointing a telescope at it and seeing a cluster sitting there. In 2017, a team mapping hydrogen gas through the zone of avoidance found a previously uncatalogued galaxy cluster, later named the Vela supercluster, sitting behind the disk at a distance of roughly 800 million light-years and contributing yet another layer to the overall peculiar velocity picture. The accounting for what's actually pulling the local universe in the direction it's moving keeps getting more complicated the more of the zone of avoidance gets pierced by new surveys. The Milky Way has been moving toward the Shapley-Norma region at several hundred kilometers a second throughout the entire history of human civilization, all while Earth's surface weather changed, empires rose and fell, and the night sky looked exactly the same every clear evening to everyone who looked up. There's something almost meditative about that. A motion too large and too slow to feel, too constant to interrupt, running underneath everything else this planet has ever done. And yet the distance to all of this mass hasn't been shrinking. We are moving toward the Great Attractor region, and have been for billions of years, and we are no closer to it than we were. There's a reason for that, and it's the same reason that eventually ends every gravitational story in the universe at large enough scale. What's carrying everything away faster than gravity can pull it back? For most of the 20th century, physicists assumed that if the universe was expanding, gravity must be slowing it down. The logic was simple. Every galaxy pulls gravitationally on every other galaxy, and even across billions of light-years, all that mutual attraction should work as a brake, gradually reducing the rate at which space grows over time. Nobody thought the expansion would stop or reverse, at least not in the near future, but most people assumed the rate would be measurably decreasing, the way a ball thrown upward slows as it rises. Measuring exactly how much it was slowing down was considered a clean observational project, one that would nail down the long-term fate of the universe with some precision. Two independent teams set out to do exactly that in the 1990s, using a specific kind of stellar explosion as their measuring tool. When a particular type of star accumulates mass past a critical limit and becomes unstable, it ignites in a thermonuclear explosion precise enough to use as a standard candle, a blast that always reaches nearly the same peak brightness, regardless of where in the universe it occurs. Measure how bright the explosion actually appears from Earth. Compare it against how bright it should appear at the known peak output, and the dimming tells you exactly how far away the explosion happened. Saul Perlmutter led the supernova cosmology project at Berkeley. Brian Schmidt and Adam Rees led the High-Z supernova search team working independently. Both groups were looking at supernovae in distant galaxies, far enough away that the light had traveled for billions of years before reaching modern telescopes, and both were expecting to find that the distant supernovae appeared slightly brighter than a uniformly expanding universe would predict, since gravity should have been slowing things down and making the universe denser in the past than the current rate would suggest. They found the opposite. The distant supernovae were fainter than expected, not brighter, meaning they sat farther away than a universe decelerating under gravity's influence should have placed them. The expansion wasn't slowing down, it was speeding up. Space between galaxies was growing faster now than it was billions of years ago, and whatever was driving that acceleration wasn't anything either team had looked for when they started their observations. Perlmutter, Schmidt, and Rees shared a Nobel Prize in 2011 for the discovery. It's worth noting how thoroughly unexpected the result was. Both teams initially suspected they had made an error. The data from one team was checked by the other specifically because neither group was willing to accept their own numbers without independent verification. Both came back with the same answer. What's causing the acceleration doesn't have a satisfying explanation yet. Physicists have given it a working label: dark energy, defined operationally as whatever is responsible for the observed accelerating expansion, without any consensus on what it actually is at a deeper level. The simplest description, and the one currently best supported by observational data, treats it as a fixed property of empty space itself, a kind of outward pressure built into the vacuum rather than carried by any particle or field. Einstein's original equations actually had a term with exactly this character, a cosmological constant he introduced and then removed when measurements seemed to suggest a static universe. That constant, reinserted with the opposite sign from what he originally used, now sits at the center of the standard cosmological model, carrying 68% of the total energy budget of the observable universe. Ordinary matter, everything made of atoms anywhere, accounts for roughly 5%. Dark matter accounts for roughly 27%. The remainder, the dominant component of everything, is this pressure that currently has no confirmed microscopic explanation. The geometry of what's actually happening to space itself is worth being careful about. When a galaxy recedes from us as the universe expands, it isn't moving through space toward some distant wall. Space itself is growing between us, new distance being generated between every pair of points rather than either point moving through a fixed background. The analogy that gets used most often, dots on the surface of a balloon being inflated, gets the topology roughly right but fails in one specific way. A balloon has a center inside it, a place the surface is expanding away from. The universe has no equivalent center. Every point in it sees every other point receding, all simultaneously, because the expansion is uniform everywhere rather than originating from one location. That distinction matters when you ask whether distant galaxies can eventually move away from us faster than light. They can, and many already have, not by traveling through space at superluminal speed, which special relativity prohibits for any object moving through space, but because the space between us and them is being generated faster than light can cross it. The observable universe has an edge not because space ends there, but because light from beyond a certain distance can never reach us regardless of how long we wait. Anything beyond roughly 46 billion light-years is already beyond that edge, even though it's all still part of the same universe. Anything that's currently close enough to see but sitting far enough that expansion will eventually carry it past that threshold will eventually vanish from our observable sky, its light redshifting toward zero frequency before it disappears entirely. That threshold is already being crossed. Galaxies and distant clusters we can observe tonight are already moving beyond our cosmic horizon, their light traveling toward us for billions of years before eventually losing the race against the expanding space it has to cross. The light from those galaxies is still arriving. For now, still technically visible to telescopes sensitive enough to catch it. But we will never learn anything new about them, because no new information will ever close the gap between us again. The last light they ever send us is already in transit. We just haven't received it yet. There is, as yet, no confirmed measurement indicating that dark energy changes over time rather than remaining constant. Several researchers have proposed that it does vary, a concept sometimes called quintessence, and some recent analyses of large-scale structure have suggested mild hints of variation that don't yet rise to the level of a confirmed detection. If dark energy does vary with time, that would have direct consequences for the discrepancy between different methods of measuring the universe's expansion rate, since a non-constant dark energy could change the expansion rate history in ways that shift the two families of measurement into better agreement. That possibility remains open, neither confirmed nor ruled out, and is the subject of active ongoing study. Whatever dark energy actually is, its presence means the large-scale story of the universe ends with isolation rather than collapse. Structure doesn't stop forming locally. The Milky Way and Andromeda will still merge. The local group will still hold together. But the distance between the local group and everything outside it will grow without limit, every other galaxy eventually disappearing beyond the observable horizon, leaving the merged remnant of our local cluster alone inside an expanding emptiness it can never cross. The race the universe is running is one that gravity cannot win at large enough scale. That changes the question of what the largest things gravity has managed to build actually are, and how long they have left to hold together before expansion carries them too far apart to matter. There's a rule built into modern cosmology that almost never gets stated explicitly, but that the entire model depends on. It's called the cosmological principle, and it says that when you average the distribution of matter across large enough volumes, the universe should look the same from every point within it. Not identical at every location, since stars exist in some places and not others, galaxies exist in some places and not others, and everything we've traced in this story has been structured web of filaments and voids that makes the universe anything but uniform at local scales. But above a certain threshold of scale, those local variations should average out. The universe should become statistically smooth, the way a glass of water looks uniform even though the individual water molecules inside it are in constant chaotic motion. Pull back far enough, and structure should dissolve into sameness. The threshold where that smoothing is supposed to happen has been estimated in various ways over the decades, but the most commonly cited range puts it somewhere between 300 and 500 million light-years. Above that scale, the argument goes, any region of the observable universe should look statistically indistinguishable from any other, with roughly the same average density, the same average distribution of galaxies, and no coherent structure spanning from one end to the other that would make one patch of sky meaningfully different from the opposite patch. This isn't an arbitrary assumption. It's a testable prediction of the standard cosmological model, and it matters because the model's entire account of the universe's history, including its description of dark energy and the expansion history just covered, is built on the assumption that the cosmological principle holds. The practical test for whether this threshold is being respected runs through galaxy surveys. Map enough galaxies with enough precision and measure their three-dimensional positions, then calculate how matter clumps at different scales. If the cosmological principle holds, the measured clumpiness should drop off towards zero as you go to larger and larger scales, the distribution becoming effectively random above the threshold. Several surveys over the past 2 decades have produced results broadly consistent with that picture, while also finding structures at the upper boundary that have kept the question alive. The Euclid telescope, launched in 2023, and the Dark Energy Spectroscopic Instrument Survey currently underway, are mapping hundreds of millions of galaxies specifically with the precision needed to test the homogeneity threshold more rigorously than any prior survey could. The problem is that as surveys have gotten larger and more detailed, they've found structures that push uncomfortably close to, and in some cases appear to exceed, the scale where the universe was supposed to have already smoothed out. The Shapley supercluster, already encountered as a gravitational source earlier in this story, extends across a region roughly 500 million light-years across, sitting right at the upper end of the range where homogeneity should be setting in. By itself, it doesn't break the cosmological principle definitively, since it sits at the boundary and its total density contrast is within the range the model might still accommodate. But it's one of several structures at this scale that, taken together, have made the question of whether the homogeneity threshold is being respected feel less settled than it appeared 2 decades ago. In 2024, a team of researchers reported a candidate structure of a different magnitude entirely, identified by mapping the positions and recession velocities of thousands of galaxy clusters across a large region of sky and looking for coherent groupings too large to be random. The structure they found, which the researchers named Quipu after the knotted cord used by Andean civilizations to record information, spans an estimated volume possibly exceeding 1 billion light-years across, making it one of the largest candidate structures yet proposed. Its status is still being evaluated by the broader community. The original paper hasn't been refuted, but structures of this proposed scale require extensive independent confirmation before they settle into the accepted catalog of known objects, and that process takes time. What's worth understanding about cases like this isn't just the size, it's what the size implies about the cosmological principle. If a structure spans a volume large enough that the universe hasn't smoothed out at that scale, 2 possibilities sit on the table. Either the cosmological principle is approximately correct, but the homogeneity threshold is simply higher than current estimates, requiring a revision rather than an overthrow of the model, or the principle itself is more deeply wrong than a simple upward revision would fix. Distinguishing between those 2 possibilities requires more and better data than exists right now, and is one of the active research areas driving next-generation survey design. The philosophical shape of this problem mirrors something covered much earlier in this story, and the symmetry is worth making explicit. When we followed matter down to the smallest possible scale, we found a floor, the Planck length, below which the concept of a defined position stops working, where space itself refuses to be divided any further and returns only uncertainty when asked for a location. What we're encountering now at the largest scales is the ceiling version of the same collapse. The concept of a single coherent object requires some shared causal history, some physical process that bound the parts together, some observation that confirms the whole thing is connected, rather than simply appearing that way from a particular vantage point. At 1 billion light-years of extent, no signal has had time since the Big Bang to travel from one end of the proposed structure to the other and back again, meaning no physical process could have organized the whole thing into a coherent entity in the way smaller structures were organized by gravity over billions of years. At that scale, calling something a single structure is partly a statistical description of a correlation in data and only partly a statement about physical unity. The word object starts to lose its grip, not in the same direction as it did near the Planck scale, but for the same underlying reason. The concept was built for a range of scales, and at both ends of that range, it quietly breaks. The cosmological principle, if it holds, saves us from having to answer the hardest version of this problem. If the universe really does become statistically smooth at large enough scales, then the filaments and superclusters we've traced are real but bounded, local fluctuations riding on top of a uniform background. If the principle breaks, then the background itself is structured in a way the standard model didn't predict, and the account of the universe's history that underpins almost every number in this story needs revision of a kind nobody has yet scoped out. Both possibilities are live. Neither one has been closed. If the concept of a single structure is already strained at 1 billion light-years, the next question is whether anything in the data has already crossed that line completely, producing something measured and published and real that the existing framework has no comfortable way to accommodate. The theoretical maximum size for a coherent large-scale structure, derived from the cosmological principle and the time available since the Big Bang, sits at roughly 1.5 billion light-years, perhaps a bit more depending on the specific assumptions built into the calculation. The basic logic runs as follows. Structure in the universe grows through gravitational instability, small overdensities amplifying over time as they pull in surrounding matter and dark matter scaffolding, building filaments and clusters across billions of years. For a structure to be truly coherent, some physical process must have connected its parts, and no physical process can propagate faster than light. The universe is about 13.8 billion years old. The earliest structure formation happened hundreds of millions of years after the Big Bang, which means gravity has had somewhere around 13 billion years to work on building things. At the speed of light, that's roughly 13 billion light-years of maximum reach, but reaching implies the full round-trip signal, the organizing influence traveling out, and the response coming back, which cuts the effective causal range roughly in half. 1.5 billion light-years is a rough estimate, not a precise cutoff, but it's grounded in physics that's been tested extensively at smaller scales. Gamma-ray bursts are brief, intensely energetic explosions detectable across enormous distances, far greater distances than ordinary galaxy surveys can easily probe, making them useful tracers of where matter was concentrated in the distant past. A research group led by Istvan Horvath published an analysis in 2013 and refined it in 2014, mapping the positions of known gamma-ray bursts across a particular region of sky and asking whether they clustered more than random distribution would predict. They found a region spanning roughly 10 billion light-years across, where the burst rate was statistically elevated, a concentration too dense to dismiss immediately as chance variation. They named it the Hercules Corona Borealis Great Wall, after the constellations marking its boundaries on the sky. 10 billion light-years is roughly 10% of the entire observable universe's diameter. It's also roughly 7 times larger than the theoretical maximum just described. The limit, gravity, and time together should have imposed on anything organized enough to call a single structure. If the detection is real and the interpretation holds, it means something spanning 10 billion light-years formed coherently, which would require either a physical process operating faster than the constraint allows, a violation of the cosmological principle deep enough to restructure our understanding of how matter organized in the early universe, or some combination of initial conditions that the standard model doesn't currently accommodate. Gamma-ray bursts are rare events, detected one at a time over decades of observation. The sample of bursts in the relevant region of sky is large enough to produce a statistically significant clustering signal, but not large enough to nail down the structure's precise boundaries or confirm its extent by multiple, independent methods. The signal sits at a confidence level that would be considered strong in many fields, but falls short of the threshold particle physics sets before treating a discovery as settled, and gamma-ray burst surveys carry their own detection biases that are harder to control than galaxy position surveys. Several independent groups have reanalyzed the data since the original paper and come to different conclusions about the statistical significance, with some finding the clustering robust and others arguing the sample is too small to distinguish real structure from statistical noise. No consensus has been reached. The usual path for a contested astronomical detection is more data, better surveys, cleaner statistics, and eventually a determination of whether the signal holds. For a structure at this scale, more data will eventually sharpen the picture. But even before that happens, the theoretical problem it poses is real and independent of the statistical question. If the universe's matter is distributed in a way that produces 10 billion light-year scale correlations in the positions of gamma-ray bursts, that fact requires explanation regardless of whether those correlations add up to what we'd call a single structure in the strict sense. Something in the distribution of matter at this scale is behaving differently from what the cosmological principle predicts, and the explanation for that behavior doesn't change depending on whether we name the region a structure or decline to. The time problem is where the deepest difficulty sits. Structure formation models have been tested thoroughly at scales up to a few 100 million light-years and found to match observations well. At those scales, the models correctly predict how dense regions grew from the tiny fluctuations seeded in the very early universe, how dark matter halos formed and merged, and how the observed filament and void pattern emerged over time. Extending those models to 10 billion light-year coherence doesn't just require tweaking a parameter. It requires either a very different initial conditions picture, one where the early universe contained correlated fluctuations over scales our current inflationary models don't produce, or a physical mechanism that can organize structure at those scales faster than gravity acting alone allows. Nobody has proposed a fully worked-out mechanism that accounts for both the smaller scale successes and a 10 billion light-year coherence in a single, consistent framework. The actual range of possible explanations splits roughly into three kinds. The first is that the detection is real, but is being misread as a single structure when it's actually a statistical correlation between several distinct but loosely associated concentrations that happen to lie in the same broad region of sky. The second is that the detection is real and does reflect something at that scale, which would mean initial conditions in the very early universe were correlated over lengths our current inflationary models don't predict, requiring a revision to the picture of what happened in the universe's first fraction of a second. The third is that the detection will eventually fail to hold up as surveys improve and the statistical significance turns out to have been driven by sampling effects rather than real clustering. All three remain live possibilities. What none of them allow is for the physics of structure formation itself to simply work faster than the available time. That constraint comes from well-tested physics, not from an assumption specific to any particular cosmological model. If something coherent by physical definition spans 10 billion light-years, the time available to build it is the one constraint the universe doesn't negotiate. After encountering two structures in a row that strain or appear to break the theoretical size limit, a reasonable question surfaces about how confident anyone should actually be in the distances being cited. If the numbers are uncertain, the violations might not be violations at all. How exactly do we know that any of these distances are what we say they are? Every distance cited in this story rests on a chain of methods, each one calibrated against the one below it, with no single method able to reach all the way from the smallest scales to the largest without borrowing reliability from its neighbors. The chain has a name, the cosmic distance ladder, and understanding it is the only honest way to evaluate how much trust any of the numbers in the previous few hours actually deserve. The bottom rung is geometry, and it's the only rung with no dependence on assumed physics. Parallax measures the tiny apparent shift in a nearby star's position when observed from opposite sides of Earth's orbit, using nothing more complicated than trigonometry, the same trigonometry used to survey land or calculate the height of a building from a distance. It works. It's been verified independently at every opportunity technology allows, and it doesn't require any assumption about the nature of stars or the behavior of light beyond the most basic geometry. The Gaia satellite, introduced earlier in this story, has extended this purely geometric baseline to cover more than 1 billion stars, building the most reliable foundation any astronomical measurement chain has ever had. The limitation of parallax is equally simple. The apparent shift gets smaller as the star gets farther away, and at large enough distances the shift becomes too small to detect, even with the best instruments. Gaia's reach caps out at roughly a few tens of thousands of light-years, which sounds enormous until you remember that the observable universe extends billions of times farther than that. The next rung uses those geometrically confirmed stars to calibrate a different kind of measurement tool, the Cepheid variable stars, whose pulsation period relationship Henrietta Swan Leavitt identified from the Magellanic Clouds more than a century ago. Knowing the geometric distances to nearby Cepheids from parallax and knowing their pulsation periods allowed astronomers to pin down the exact relationship between period and true brightness. That calibrated relationship can then be applied to Cepheids in distant galaxies, too far away for parallax to reach, translating their observed periods into true brightnesses and therefore into distances. This rung reaches out to roughly 100 million light-years, far enough to begin mapping the large-scale structure of the local universe. Type Ia supernovae extend the ladder further, which is why the teams whose 1998 discovery launched the dark energy era used them for a job that Cepheids couldn't reach. Supernovae are bright enough to see across billions of light-years, and their peak brightness, though not perfectly identical, is consistent enough, after a correction based on how quickly the brightness fades, that they function as reliable standard candles at distances no other stellar tracer can match. Calibrating them requires anchoring their intrinsic brightness against Cepheid measurements in the same host galaxies, which in turn rests on the geometric parallax baseline below. The full chain starts with geometry pinning down Cepheid brightness then calibrating supernova brightness, and supernova brightness finally reaching across the observable universe. At the very top of the ladder, no individual objects are resolved at all. Redshift takes over. As the universe expands, light traveling through it gets stretched, shifting toward longer, redder wavelengths in proportion to how much space has expanded since the light was emitted. Measure a galaxy's redshift, and you know how much the universe has grown since that light left it. Convert growth factor to distance using the expansion rate, and you have a distance measurement that in principle reaches anywhere in the observable universe. The conversion factor is the Hubble constant, the number that relates recession speed to distance, and it's where the chain's most significant current problem lives. Two families of measurements now give different values for the Hubble constant, and the disagreement has grown more pronounced as both methods have improved. Measurements anchored to the cosmic microwave background, the pattern of temperature variations imprinted across the whole sky from the universe's infancy, consistently return a value around 67 kilometers per second per megaparsec. Measurements built up from the local distance ladder, using parallax to Cepheids to supernovae to nearby galaxy recession speeds, consistently return a value around 73 kilometers per second per megaparsec. Both values have been checked multiple times by independent groups using different instruments. Both uncertainties have shrunk as the data improved, and the disagreement between them has grown rather than narrowed, now sitting at roughly 5 standard deviations, far past the point where statisticians are comfortable attributing it to chance. This is the Hubble tension, and it represents the weakest link in the chain. The two families of measurement are not checking different versions of the same thing. The CMB method infers what the Hubble constant should be based on the full physics of the early universe and the standard cosmological model, predicting a value from the conditions of the universe's infancy that should match the locally measured expansion rate if the model is complete. The local ladder measures the expansion rate directly, without assuming any particular cosmological model. If both measurements are right, the model connecting early universe conditions to late universe expansion has a gap in it that nobody has filled. One family of proposals involves systematic errors somewhere in the distance ladder, a miscalibration that hasn't been caught because the different rungs don't overlap directly at every point. A second family proposes new physics in the early universe, an extra component of energy that briefly sped up the expansion in the universe's first 100,000 years before disappearing, leaving the CMB measurement slightly off in a direction that would close the gap. A third possibility connects to the mild local underdensity mentioned several sections ago, which would make local measurements systematically different from the cosmic average in a way that shifts the ladder value upward. None of these have been confirmed. The tension is real and unresolved, and it sits at the heart of the most actively contested area in current observational cosmology. One new rung is being added to the ladder from a completely different direction. Gravitational wave detections from merging black holes and neutron stars provide an independent way to measure distances using the shape of the wave signal itself to calculate how far away the merger happened without relying on any optical calibration whatsoever. The method is called standard sirens, parallel in logic to standard candles but using space-time ripples instead of light. Current gravitational wave detector networks have made dozens of detections, and the standard siren distance measurements are still too few and too uncertain to resolve the Hubble tension definitively. But the precision is improving with each detection, and the sample is growing. Within the next decade, this independent rung may be accurate enough to determine whether the tension is a systematic error or a signal of missing physics. A tension in the Hubble constant doesn't invalidate those distances outright, since most of them are confirmed using methods well below the point where the tension operates. But it does mean the full framework connecting small-scale measurements to the universe's largest scales has a visible seam in it, a place where two reliable measurement traditions currently disagree, and the structures sitting near that seam carry an honest uncertainty that the distances to nearer things don't. With the measuring tools now visible, and the limits of what they can confirm laid out honestly, one question sits underneath everything in this story. What are the things being measured actually made of? Every element heavier than hydrogen and helium had to be built somewhere before it ended up anywhere. It wasn't delivered with the universe. When the Big Bang cooled enough to allow the first nuclei to form, roughly 3 minutes after the start, the result was almost entirely hydrogen, about 75%, and helium, about 25%, with trace amounts of deuterium and lithium scattered through. That's the full inventory of what the early universe made on its own. Carbon, oxygen, nitrogen, calcium, iron, phosphorus, everything else that shows up in a chemistry textbook or a periodic table or a living cell, none of it existed yet. The universe ran for millions of years on only those first few elements. The first stars formed from that hydrogen and helium, pulled together by gravity in regions where the gas was slightly denser than average, compressing under their own weight until the cores grew hot and dense enough to ignite fusion. These first stars, sometimes called population 3 stars, left no confirmed survivors and haven't been observed directly, but their composition can be inferred from the chemistry of the oldest surviving stars and from theoretical models of the early universe. They were massive by modern stellar standards, burning hot and fast, exhausting their fuel in a few million years rather than the billions that a sun-sized star takes. Hydrogen nuclei fused into helium, releasing energy that pushed outward against the inward pull of gravity and held the star stable. In stars large enough to have hot enough cores, an additional pathway called the CNO cycle accelerated that same hydrogen fusion by using carbon, nitrogen, and oxygen as catalysts rather than as end products, cycling through them to produce helium more efficiently than direct proton-proton fusion alone. That stability was never permanent. Burning through the hydrogen in a star's core eventually left a helium-rich core that could itself compress and heat until helium nuclei began fusing into carbon and oxygen. The process continued through successive shells of heavier fusion in large enough stars, carbon burning to produce neon and magnesium, then oxygen burning to produce silicon, then silicon burning in a final stage that ran for roughly a day before producing iron. Iron is where the process forced to stop, not because the star ran out of material, but because iron is the most tightly bound nucleus in nature. Every fusion step from hydrogen to iron releases energy because the products are more tightly bound than the ingredients. Iron can't be fused into anything more tightly bound. Trying to fuse iron absorbs energy rather than releasing it, and when an iron core accumulates in the center of a massive star, it can no longer support its own weight. The core collapses in less than a second, reaching nuclear density almost immediately, and the resulting rebound drives one of the most energetic events the universe produces, a supernova explosion that briefly outshines the entire galaxy, containing it and disperses into space, everything the star spent millions of years building. Elements heavier than iron, gold, uranium, iodine, the full suite of elements above iron on the periodic table, couldn't be produced by any fusion sequence, since fusion past iron costs rather than releases energy. They form through a process called rapid neutron capture, or the R process, where a nucleus absorbs neutrons so fast that the resulting unstable intermediate doesn't have time to decay before absorbing another. This requires an extreme neutron density that only exists during a supernova or during the merger of two neutron stars. The gravitational wave detection from two merging neutron stars in 2017 allowed astronomers to watch the production of heavy elements directly for the first time, catching the optical afterglow called a kilonova and identifying the spectral signatures of gold, platinum, and strontium being synthesized in real time. The atoms that ended up in a human body didn't travel directly from any single stellar explosion to here. The process ran multiple times over. The Sun is a third-generation star, meaning the cloud of gas and dust from which it and the rest of the solar system formed had already cycled through at least two previous generations of stars, each one building heavier elements, exploding, contributing to the diffuse gas of the galaxy, and eventually collapsing again into a new stellar system. The carbon in a person's cells was forged in a star that died long before the Sun existed. The oxygen came from a different source entirely, or possibly several. The iron in blood has a history reaching back before any planet in this solar system existed, synthesized in cores that burned for millions of years and then were destroyed in a moment. The forces involved are not different from the ones described at the start of this journey. The strong nuclear force that holds quarks together inside a proton and holds protons and neutrons together inside a nucleus is doing exactly the same work inside every atom in this room as it's doing inside every atom in the most distant galaxy surveyed by any telescope. Electromagnetic repulsion, the force that stops a hand from passing through a surface, operates between the electrons in your skin and the electrons in everything you've ever touched, the same fundamental interaction at the same coupling strength everywhere in the observable universe. The Planck length floor, the point below which the concept of distance stops working, runs underneath every atom in your body the same way it runs underneath every atom in the Shapley supercluster or in any filament traced by any large-scale survey. There is no distance small enough and no structure large enough to require a different set of rules. That shared rulebook is why the distance ladder works at all. If the physics of nuclear transitions in a carbon atom on Earth were different from the physics of the same transition in a carbon atom in a galaxy at the edge of the observable universe, spectral lines would shift in ways that couldn't be accounted for by redshift alone, and the entire measurement chain built from those lines would return inconsistent results. Instead, it returns consistent results, with a single noted exception of the Hubble tension, which itself suggests a gap in our model of the universe's expansion history, rather than a difference in the underlying physics. The atomic physics is the same. The nuclear physics is the same. The electromagnetic and gravitational interactions are the same. The evidence for that consistency isn't philosophical. It's built into every reliable measurement in this story. You're in a direct and literal sense the same material as the things examined across this entire journey. Not metaphorically adjacent to them, not spiritually connected to them, but made of the same protons and electrons and quarks, governed by the same fields, sitting at the same Planck scale floor, forged in the same nuclear processes that lit the stars we've been measuring distances to for the last several hours. The distance from the smallest thing physics can describe to the largest structure astronomy has confirmed spans 60 or so orders of magnitude, and you sit somewhere in the middle of it, assembled out of the same inventory the rest of it runs on. Nothing in this story was about something foreign to you. It was all a description of the same thing, at different scales. Where does that leave us right now, in this room, in the dark? The room you're in right now is a specific place, in a specific structure at a specific scale, and we've spent this whole journey building up to being able to say exactly what that means. You're somewhere in the middle of a range of sizes that runs from the Planck length, at the smallest end, where position and distance dissolve into uncertainty, to the Hercules Corona Borealis Great Wall, and structures like it at the largest end, where the concept of a single connected object starts to lose its grip. That range spans roughly 60 orders of magnitude. You sit at around the 20th rung from the bottom, in the narrow band where an object can still be one thing, where it has a location you could point to, a boundary you could in principle draw, a size that means something physically rather than statistically. The body you're resting in is exactly the kind of thing the word object was built to describe. At smaller scales, the word starts to fail. At larger scales, it starts to fail again. You're at the right scale for all of this to hold together. The breath moving through your lungs right now is carrying oxygen atoms that were forged in a star that died before the sun existed. Not like those atoms. Those exact atoms, or atoms built through the same process in the same kind of nuclear furnace, by the same strong force that holds the quarks together in every proton in your body. Exhale, and you're returning carbon dioxide built partly from carbon atoms, with a history stretching back to a stellar core that collapsed before any planet in this solar system existed. The transaction is ancient and continuous, and happening right now in the dark. The iron in your blood carries a similar history. Hemoglobin holds iron at its center, and that iron was produced in the silicon-burning shell of a massive star in the final day before the star's core collapsed. The same collapse that scattered that iron into the interstellar medium, into the molecular cloud that eventually formed the sun and everything orbiting it, including the planet under you right now, including the body on top of that planet. The heartbeat moving that iron through you is powered by chemical energy stored in bonds between carbon, hydrogen, oxygen, and nitrogen atoms, all of them built in stars, all of them governed by the same electromagnetic force that stopped your hand from passing through a surface the moment this story began. Your body temperature is thermal energy, the random kinetic motion of every atom in your tissue. And it's the same kind of energy that constitutes the majority of a proton's mass, the bound energy of the gluon field, and the constant motion of confined quarks. The distinction between the heat in your skin and the mass in a proton isn't a difference in kind. It's a difference in organization and scale. Energy stored as motion versus energy stored as confinement, the same underlying currency. The Planck floor sits under every one of those atoms right now. There's no way to get closer to it inside your body than anywhere else in the universe, because it's a floor under all of space, not under specific locations. It's there under the mattress. It's there under the planet. It's there under the Shapley supercluster, under the filaments traced by every galaxy survey in this story. The floor doesn't change with location. It's the floor of the whole thing. And where you are in the whole thing has a specific address, if you want one. On a minor spiral arm of a galaxy called the Milky Way, orbiting the galactic center at about 220 kilometers a second, in the outer edge of a supercluster called Laniakea, drifting with everything else in it toward a concentration of mass 650 million light-years away that we spent an entire section of this story tracing. In the local group, which is itself drifting toward the Virgo cluster on a trajectory it will never complete, because expansion will carry both of us away from each other before gravity gets the chance to close the gap. In the observable universe, whose edge sits about 46 billion light-years in every direction from your current location, and beyond which no information will ever reach you. None of that motion is felt. None of it is sensed. The only thing your body reports is the pressure of the surface you're lying on, the warmth of the air you're breathing, the quiet sound of the room, the slow rhythm of breathing in and out, all of it mediated by the electromagnetic force, the same one that makes objects feel solid, the same one your hand first pushed against at the start of all this. You contain roughly 7 octillion atoms. Each one has a proton with a floor below it that physics can't yet describe. Each one is part of a structure that sits at the only scale where structure clearly means what it's supposed to mean. All of it assembled from elements that had to be made before they could end up here, through processes that took billions of years and several generations of stellar birth and death, and that finished just in time for the solar system to form from what was left. It all ends here, in the dark, with a body that contains everything in this story at the scale where the word everything still makes sense. Thank you for staying with all of this tonight. I hope you sleep well.